Hello, everyone, and a very good morning to all of you. Distinguished delegates, presenters, and participants from SAARC member states and other regions around the globe. Ladies and gentlemen, I am very thankful to all of you for joining us in our first SAARC webinar in the year 2018. Firstly, I would like to introduce myself. I am Ehsan Javed and I am working at SAARC Energy Center as Research Fellow Renewable Energy for the past 4 years. I shall be moderating this 2 day session of the SARC webinar, the aim of which is to disseminate the findings of the SARC study report on use of submersible turbines in canals and the assessment of its resource potential to the policymakers, regulators, researchers, academia, and other stakeholders from the member states. The study report was conducted last year by Dr. Nawaz Akhtar, who is one of the renowned and famous experts of hydropower sector in South Asia region, and we are really blessed to have him with us today. It is also my pleasure to inform you that Dr. Shoaib Ahmed, who is the acting director of SARC Energy Center, has also joined us in this webinar. We are very thankful to you, sir, for taking out time from your busy schedule to attend this event. At the end, I am extremely grateful to all our elite panel of presenters, such as Mr. Asif Farid, Dr. Irfan Yusuf, Ehsan Marwat, Mr. Carl Comsi, Mr. Tommaso Morbiato, Mr. Asim Shehzad, and Mr. Umar Mukhtar for their enthusiasm and eager willingness to participate in our webinar. I shall introduce them in detail before the start of their relevant sessions. Ladies and gentlemen, the natural power of a running river or stream has been of interest for electricity production for many years. The technology of small, medium scale hydropower production is diverse, and different concepts have been developed and tried out. Water current turbines, which are also called hydrokinetic or in-stream turbines, have received a growing interest in many parts of the world. Two main areas where hydrokinetic devices can be used for power generation purposes are tidal currents and river streams. These turbines generate power from the kinetic energy of a flowing stream of water without the use of a dam or a barrage. Because of the low investment cost and the lack of frequent maintenance, this technology is cost effective in comparison to other technologies. A number of prototype and demonstration projects have been installed and are successfully running in different parts of the world. The major topics which shall be covered during this webinar includes the introduction, submersible turbines technology, selection of sites for the hydrokinetic submersible turbines, assessment of resource potential, planning for the installation of submersible turbines, findings, conclusions, and recommendations. And at the last, there would be given some suggested future studies or other research areas which can be recommended by the presenters. Dear participants, ladies and gentlemen, you will have the opportunity to ask questions to presenters by typing your questions or clicking to the raised hand option into the attendees pane of the main window of GoToWebinar software. You may send in your questions at any time during the presentations. We will also collect these and address them during the question answer session at the end of each presentation. Now, I would like to request Dr. Shoaib Ahmed, Acting Director, SARC Energy Center, to deliver his welcome speech. I would briefly introduce Dr. Saab. Mr. Dr. Shoaib Ahmed is an aeronautical engineer with two master's level degrees and a PhD in renewable energies. He has vast experience in management of engineering and renewable energy projects. His professional strengths are in policy making, organizational development, engineering design, and systems engineering. He has also taught in several universities and has three internationally published research papers to his credit. He is a member of many professional bodies. So now I would request Dr. Shoaib Ahmed Saab for his some welcome words. Dr. Saab, over to you.
Well, thank you, Asian. My dear friends, participants, and the presenters of the webinar. Assalamu alaikum and a very good morning to you all. I, Dr. Shoaib, on behalf of SARC Energy Center, Islamabad, welcome you all to this webinar which is about the use of submersible turbines for the generation of energy, mainly electrical power, and assessment of this technology for the SAARC region. It's a great honor for me to speak to you on this occasion and over an important technical topic which is expected to play its role in the future development and prosperity of the people of the SAARC region. Dear participants, first of all, allow me to briefly speak about the SAARC Energy Center and its responsibilities. The inception of the center as a regional institute and a technical arm for the SAARC Organization on Energy Matters was approved in year 2006. Besides, the center was expected to translate the energy vision of the SAARC leadership into reality. Therefore, a governing board, equally represented by the energy professionals from all 8 member states, was constituted to guide and supervise the center. The day-to-day functional control of the center lies with the SAARC Secretariat. Pakistan, being the host country, shares the major portion of the financial budget. The center started its operations in year 2008. During the last 10 years, the center has emerged as a vibrant and effective SAARC institute which has played its role in all regional level energy initiatives. Until 31st December 2017, the center has carried out 100 plus interventions. The reports of these interventions are available on center's website free of cost to any. Moreover, hard prints of these reports can also be asked from the center, which we shall gladly do. Today's webinar is the first in current year. We intend to hold few more on some other important technical topics. Your participation in those is solicited. Dear participants, as we all realize that energy is basic in economic development and well-being of the people. Thus, availability of commercial energy supplies at affordable prices is a key factor in economic and social growth. South Asia is not exception to this reality. Like other parts of the world, the demand for energy is ever increasing in the SAARC region as well. Unfortunately, all SAARC member states are facing acute shortages of energy. Also, in each member state, a substantial portion of the national population does not have access to commercial energy supplies, including electricity. In this grim situation, the good news is that South Asia region is abundantly blessed by the nature with the resources of conventional and unconventional energy. Furthermore, leadership of each member state of SAARC is fully committed and pursuing very hard to overcome its energy issues. In doing so, development of indigenous energy resources is a cornerstone in national energy policies of all member states. Dear participants, man has been harnessing the energy of flowing water since ages. The idea of making use of kinetic energy of water in canals and rivers is also not new. However, due to some distinct advantages and economic benefits, it's gaining fresh attention in many parts of the modern world. especially in small scale applications for provisioning of electricity to small households situated close to the canals and rivers. In my view, some typical advantages of this technology are low investment cost, easy and rugged nature of the technology, 24/7 availability of energy, independence from the national grids, and almost zero operational costs. These and similar advantages merit the need to look into the potential of this technology for the SAARC region. In this regard, learning from the experiences of the advanced world shall reduce the amount of effort, time, resources to be put in by the SAARC nations for the assessment and deployment of this technology. Such learning is possible through sharing of knowledge by the experts from the other parts of the world and subsequently by transfer of technology arrangements. Today's webinar is a step in this direction. Dear participants, last year SAARC Energy Center along with its partners conducted an in-house study on use of submersible turbines for the generation of electrical power from the flowing water in canals. The study was based on a 5 kilowatt turbine made by Mrs. Smart Hydro of Germany to be installed in the Upper Jhelum Canal. This canal is situated in the province of Punjab, Pakistan. In the study, the expert calculated the resource potential of the canal based on some assumptions and limitations as a role model to explore, identify, assess, and exploit such renewable resources available in most of the other SAARC member states. In today's webinar, we shall share with you the knowledge generated during the study as well as advanced knowledge available in other parts of the world. Another very important objective of this webinar is to learn from you all, not on this particular technology, but also as a whole on working of the SAARC Energy Center and how to make it more effective. In this webinar, we have invited regional and international experts. I am delighted to acknowledge the great cooperation and support extended by all of them in this regard. This depicts their resolve and commitment to the cause of energy and making it available to those who do not have it. In the end, I once again thank you all for joining this webinar and shall request you to feel free in suggesting us any improvement in the working of the center. Tomorrow in the afternoon, we have a special session in this regard. I would also extend my special thanks to the experts and the presenters of the webinar, as well as Punjab Irrigation Department, Institute of Space Technology, Islamabad, and other partners of the center who contributed in the last year's study. Lastly, I wish you all a very comfortable learning and knowledge sharing in this webinar. May God bless people of South Asia and give us strength to serve them better. Thank you very much and best of luck. Thanks.
Well, thank you very much, Dr. Shoaib Ahmed Saab, for your very nice reviews and welcome message to all the presenters and all the participants. We are thankful to you, sir, for your time. And now let's presenters and participants, let's kick off with our main agenda. We have on our agenda the first presentation on introduction of the hydrokinetic submersible turbines. The presentation would be delivered by Mr. Ehsanullah Marwat. I would briefly introduce Mr. Ehsanullah Marwat. He is an engineer. Engineer Ehsanullah Marwat is working as research fellow energy efficiency in SARC Energy Center. He has a unique blend of specialities. Apart from graduation in mechanical engineering, he has two specializations to his credit, one in energy management and the second in environmental engineering. Currently, he is pursuing his PhD in Energy System Engineering from a US Pakistan Center for Advanced Studies in Energy, National University of Science and Technology, Islamabad. Before joining Sarg Energy Center, he has also worked as energy and environment expert in the housing department of Government of Khyber Pakhtunkhwa. Earlier, he worked with an energy consulting firm as manager projects. He has a diverse experience of about more than 15 years in various segments of energy sector, mainly in hydropower generation, solar energy, energy management on the demand side, energy audits, and oil and gas, particularly in CNG sector. He has remained part of many prestigious projects through feasibility studies, economic analysis, environmental studies, including EIS and IEEs, energy management, as well as monitoring and evaluation. Mr. Ehsanullah Marwat, we are very thankful to you for agreeing to give presentation on such an important topic. We would kickstart with you and over to Mr. Ehsan Marwat for his presentation. Mr. Ehsanullah Marwat would start his presentation in 30 seconds time. I think he is having some difficulty with his microphone. In the meanwhile, I would like to explain in detail again that all the participants and all the experts, they can really ask questions at any time of the presentation. They can either ask questions by writing us the question in the chat mode, or secondly, they can raise their hands if they want to ask it verbally. We would give them time during the after the presentation in the or question answer session. Plus, additionally, if there are any additional questions, you can write to us via email. You can also send us those questions to us, and we can address them at the end of the second day, where we have a very detailed session on the knowledge sharing session at the end of the second day webinar. So I think Mr. Ehsan Marwat is now ready for giving his presentation. Ehsan Saab, over to you. Thank you very much.
Okay. Before starting, Ahsan Saab, you first confirm me that at least you hear me.
Yes, sir, you are audible, and I think your presentation is also clear. You may need to broad it up. It's very in a very small mode, so you can just put it on the full screen, and then over to you.
Sir, with me, it's on the full screen mode.
Okay, perfect. Go ahead, sir.
Okay. Well, thank you very much, Ahsan Saab, and thank you for confirmation that I'm audible. So once again, thank you very much for this detailed introduction. Anyways, guys, hello everyone, and a very good morning. I welcome you all here in this webinar being organized by SARC Energy Center. I'm really thankful to the center as well. Well, as introduced by Mr. Ehsan and as displayed on screen, I'm Ehsanullah Marwat. I'll be having my presentation on, I'll be giving you guys a small introduction on hydrokinetic submersible turbines. Since I was having a glance over the list of participants, there is a variety of participants with diverse background. I will try to keep my pace and level little moderate so that those with lesser familiarity with the hydrokinetic technology can also go along us. So Let's start with some basics. There might be some confusions in some people that what is the difference between hydropower and hydrokinetics. But let's see how actually hydrokinetic is different than hydropower. Well, they can be differentiated in many aspects, like major distinction is based on the form of energy that both these systems uses for conversion. That is the potential energy in terms of hydropower and kinetic energy in case of hydrokinetic. But here I tried to highlight the difference based on structural aspect in order to cover the environmental aspect as well. So guys, we know that to harness hydropower, whether it be a dam or the case of a runoff river project, we make huge structural changes in the water body and its surroundings. Whereas in comparison for hydrokinetic, to be, it's well, I can say it is as easy as falling off a log. I mean, it's relatively very simple to install. So this is my opinion of differentiating them, but obviously mainly it's based on the conversion of type of energy that is that is potential and kinetic energy. So let's come to the basic theme of our presentation. So let me share that hydrokinetic submersible turbines, which are also called water current turbines, or in some cases we called them in-stream turbines. Though the technology is new, still these turbines are getting interest in many parts of the world. Two main areas where hydrokinetic devices can be used for power generation purposes could be: number one, tidal currents or ocean waves. This is the technology that attempts to harness the energy from ocean waves or the tides. Whereas the second form is river streams or ocean currents, or you can say canal. Technology that attempts to harness energy from the river currents and streams. Although both use similar technology, we will focus mainly on river stream current. As we know that history of harnessing natural power of a running stream or a stream is quite old, when people used to grind grains and later on for electricity production for many years. Anyways, our focus in this presentation would be obviously the same for rivers. So hydrokinetic submersible turbines, as we differentiated in earlier slide, formally we can say that these turbines generate power from the kinetic energy of a flowing stream of water without the use of a dam or a barrage. Water current turbines can be installed in any flow with a velocity usually termed as a greater than half meter per second. Because of low investment costs and maintenance fees, this technology is cost effective in comparison to other technologies. The continuous supply of electrical energy is also as an advantage in comparison to solar power or other small scale renewable technologies. This kind of small scale hydropower is considered environmental friendly, meaning that the water passing through the generator is directed back into the stream with relatively small impact on the surrounding ecology. Well, small scale water current turbines can be a solution for power supply in remote areas, that is, we can say off grid applications. Because of the low cost and durability of this kind of hydropower, developing countries, particularly including SAARC member states, can manufacture and implement the technology to supply the needed electricity to small communities and villages. Well, Although to my knowledge, there is not much data on the resource potential of hydrokinetic power. Let me refer to a report by Hydrocubic. In fact, Hydrocubic is a public utility that manages generation, transmission, and even distribution of electricity in Quebec, Canada. So, according to Hydrocubic, theoretical global hydrokinetic potential of ocean and tidal currents near shorelines is 7,800 terawatt hour per year. That's roughly 40% of the world's total electricity output calculated in 2013. Whereas for river stream current potential, according to the same report by Hydrocubic, alone Canada's hydrokinetic potential is estimated to be 15,000 megawatt, from which we can have a guess of the global aspect, but actually I couldn't find some accurate figures for global level. So coming up to the concept, in fact, hydrokinetic turbines are not much different than wind turbines and are based on the same principle as wind turbines and tidal turbines, except that water is much more denser. In some cases, it's referred to be around 800 times than air. Thus, for the same velocity of ocean or stream current, would have an energy output much more than wind having the same speed. Anyways, the theory for such turbines and the science of making torque from currents was first given by Mr. F.W. Lanchester in early 1920s. Hydrokinetic turbines produce electricity directly from the flowing water in a river or a stream. Energy flux of the water stream is dependent on the density of fluid, cross-sectional area of turbine blades, and velocity of fluid cubed. Throughout the world, many different concepts have been developed to utilize this power. Well, let's discuss little about the technology and conversion approaches. Several hydrokinetic conversion concepts have been developed to date over the years. The two most common small-scale hydrokinetic turbine concepts are axial flow turbines and cross-flow turbines. If you look at figure on left side of your screen, the axial concept has a rotational axis of rotor parallel to the incoming water stream. Let me mention here the inclined axis turbines have mostly been studied for small river energy converters, whereas the horizontal axis turbines are commonly in tidal energy converters and are very similar to modern day wind turbines from design and structural point of view. Now, if we look on the right side at the cross flow concept, it is on the other hand, it has a rotational axis of rotor, which is parallel to the water surface, but orthogonal to the incoming water stream. So the advantage of cross flow turbine is that they can rotate unidirectional even with bidirectional fluid flow. Well guys, I'll not go into much details about the hydrokinetic technologies since one of my colleague will explain in detail about types and technologies of these turbines in the next presentation. So now coming to the outputs and cost, let's discuss little about these important parameters, although since the technology is relatively new, not much data is available. Anyhow, let me share that it is rare to find locations with all the right operating conditions, such as having a depth of usually dumped as the suitable depth could be at least greater than 6 meters and a current speed higher than 2 meter per second to achieve maximum, or you can say highest efficiencies. Thus, although their energy conversion efficiency is about 30 to 40%, the maximum capture rate for a stream's total kinetic energy is 15%, because a significant quantity of water is diverted around the turbine. Similarly, once this technology has reached maturity, the estimated cost of electricity generated by a river turbine is expected to be over around 15 cents per kilowatt hour. In comparison to many other technologies, particularly if we compare with renewables and green energies, hydrokinetic turbines are having more benefits with lesser environmental impacts, such as in terms of output, hydrokinetic is more predictable source of energy than wind power. No such retaining structure is required for installation of hydrokinetic turbines. Similarly, very few or almost no civil engineering works are required. Then discrete or even invisible, these turbines are invisible due to the components are near total immersion or fully immersed. There are zero greenhouse gas and atmospheric containment emissions associated during installation as well as operations. No major habitat modification, including benthic organism habitat. Similarly, no considerable modification of vegetation and possible impact on aquatic fauna is noticed. Small environmental impacts over the facility life cycles. Thank you very much. Dhanyabad, Shukriya, Kandichala. So thank you, SN Saab. Over to you. And any questions are welcome.
Thank you very much, Mr. Ehsan Marwat, for a very nice presentation. It was very informative. And to kick-start our webinar for the two-day webinar with this very introductory and very informative presentation was very nice. Mr. Ehsan Marwat has very briefly touched the theoretical potential, and we were very surprised to see this huge amount of potential in this novel technology. Then he touched the topics of conversion and operation of this hydrokinetic submersible turbines. He has also given few slides on the outputs, the energy efficiency, and the estimated cost of this producing electricity from this technology. Then at the end, Mr. Ehsan Marwat has touched on the topic of advantages and environmental benefits, which to me are very huge, even in comparison to the dam and the run-off river projects. So Ehsan Marwat Saab, thank you very much for your very nice presentation. We are thankful to you. And now we would open the window for a question answer session. So any participant who has any questions in regard to the presentation can raise their hand on the control panel. Or they, if they want to write the question, they can write on the chat and we can ask questions from Ehsan Marwat. So, ladies and gentlemen, we have our first question. The first question is from Mr. Arshad Munir. So, Mr. Arshad Munir from Pakistan has asked a question that which type of the submersible turbines is most common? I will give the mic to Mr. Ehsan Marbat for a very short answer to this question. Which type of the submersible turbine is most common?
Thank you very much, Mr. Hassan, and thank you very much, Mr. Arshad, for your question. Let me answer very briefly because the same I mentioned in my slides as well. That in fact, basically, the two common concepts are axial flow turbine and cross flow turbines. But particularly the inclined axis turbine, if I share my screen, this one.
So,
Yeah,
Sansa,
this.
do you want me to give the make you the presenter? So now you can share your screen now. Yes, please.
Oh, sorry. Okay. Actually,
Yes.
in the if you can see now the screen, as I mentioned that out of the axial flow, this inclined flow turbine is most common and mostly being studied and used in the canal system and river system for conversion of energy, the kinetic energy. This is the one inclined axis.
Yes.
So I hope.
Thank you very much, Ehsan Sab, for a very nice reply. Now we have a question from Mr. Melab Shrestha from, I guess, Nepal. He has asked a question, what do you have any experience installing this technology in Pakistan? And what is the maximum capacity installed in Pakistan? I think this question is more relevant to our main expert, who is Dr. Akhtar Nawaz, who has been
Very
implementing
right.
this project in the canal. But still, I think, to my knowledge, it is just a very novel technology, and the installation has just been kick-started now. If I'm right, you can confirm, Mr. Ehsan Sabni. Otherwise, then over to you, sir.
Yeah, very right. I totally agree. Ideally, Mr. Dr. Nawaz Saab can very rightly answer, but yes, very right. We have recently experimented a submersible turbine with us as a prototype, and he himself has supervised and monitored that turbine. If I'm not wrong, it was like in some kilowatts, maybe 5 kilowatt, and he has a good experience. And I believe better we should wait for his presentation. He has very detailed, in very thorough manner, he has explained what sort of difficulties he faced and how he has installed, what sort of environment and conditions were there when he was installing that, and even he would be able to give the technical aspects and the characteristics of that particular turbine. So I think better we should wait for his presentation.
Yes, thank you very much, Ehsan Saab, for your very brief comment on that one. So we would take two more questions. So we have a question from Mr. Hamza Khurshid. I may also request the participant to write a small note on which organization they are, so that we can also announce and we can also understand the type of question asked by the person, if he is from the academia or from a government body or private sector, something like that. So Mr. Hamza Khurshid has asked a question that could you please comment on the potential of hydrokinetic energy in the small streams in northern areas of Pakistan? I feel that this question is also relevant to a presentation at 12 o'clock today, which is on the assessment of resource potential for the selected site in Pakistan or in the region. So, but if you want to comment on that one, Mr. Ehsan, you are most welcome, please.
Yes, well, it's a very good question. And as I mentioned in my slides, that the data and the resource potential estimation is yet not very clear for the globe as well as even in the advanced world. So this was a very good initiative by Dr. Saab, Dr. Nawaz Saab, that we should calculate the resource potential, because we have a huge network of canals, not only if you talk about the Pakistan and the northern areas, but in fact, indeed, we are concerned for the whole region. I mean, the SAARC member states. So we have a huge canal system as well as river system, stream system. So that's a very good initiative, and this initiative is in fact to calculate this resource potential. So I don't think that at this initial stage we could give some exact figures, but no doubt there is a huge potential. So maybe in later presentation, one of my colleague can give a broader idea.
Yes, thank you very much, sir. We have a question from Mr. Sharing Tashi. My apologies if I am not pronouncing his name correctly. He is asked a question of: is it possible to install such hydrokinetic turbine in free-flowing river of Bhutan and other neighboring countries?
Yes, of course, sir. This is what we are targeting to. And as I just told that we are targeting for the SARC member states. Like yesterday, I was watching a video. There is like we have a small solar cells that we charge our phones with. That there are very small, even in few watts. That there are small such kind of turbines which you carry in your pocket, and you can put it in the stream, and with a relatively longer cord you can charge your phone or can light a small lamp. So that is a very basic childish or level idea, but I mean to say that it is very common and it can be applied to any moving stream, as I mentioned in my previous slide, that any flowing water and with at least half a meter per second speed. So it's very simple answer that yes.
Thank you, sir. Yes, I think that there is a lot of potential in the flowing rivers of all the South Asian countries, and that's why we conducted this study as a pilot project to assess the viability of this very novel and very new technology, and that could be replicated in other member state if that is successful. I hope so. So we have a questions from Mr. Bikash Sharma, and he has asked a question: what is the minimum depth of canal or stream required to operate this technology, although ideal depth to generate maximum power is greater than 6 meter? He is from IC mode. Over to you, sir.
Yes, yes, he's very right, and the same I mentioned that the ideal condition could be with a velocity of above 2 meter per second, 2 meter per second, and with a depth of about 6 meter. Yes, very right. But at the same time, as I mentioned for velocity, that the lowest level could be 0.5, even half meter per second. So the same is that since it's in one aspect we call it submersible. So whatever the size of the, this is I'm just talking on the common sense basis, that whatever the turbine you have and whatever the diameter or the overall size of the those blades or the turbine, the moving part, at least it should be submerged. Like if the turbine is of above 1 meter, so almost around 1 meter, so at least the depth should be above 1 meter. So this is a common sense approach, but there are also other aspects that the flow of the water is not uniform throughout the channel. It has different velocity and it moves like inverted V. So the maximum could be, the most suitable place could be the center of the canal, and it should be at least submerged. So the simple answer is that at least whatever the turbine you have, it should be at least submerged in the canal.
So thank you very much, Asan Sab. I think we are just taking the last question. This question is this technology difficult or easy from the viewpoint of the transfer of technology? I think the question concerns indigenous development or transfer of technology in a specific country. I mean, we would require to indigenously develop and manufacture this technology in future. So this question is preferably from that aspect, sir. Please.
Sir, actually, in my fourth slide, I mentioned this point as a opportunity for our region. In fact, this would be sort of my recommendations for SARC member state. As I mentioned, that SARC member states, like any developing countries, particularly most of our SARC member states are obviously developing countries and can manufacture and implement the technology to supply the needed electricity to their small communities and villages in case of off-grid options or in case of domestic supply. So obviously it is indeed the most attractive part of this opportunity. and it has no rocket science. It's very simple concept, like the same small hydrokinetic turbines which we use for potential case, the same we can with small modifications as we and at the same time, as I mentioned, that it's basically just same as wind turbines except the density difference. So you can simply say that if you put a wind turbine in a canal, it can give you this opportunity, although it's not logical solution, but just to make a case.
Thank you very much, sir. We are grateful to you for replying to these questions. And now over to, I think we are lacking behind as per our schedule because we were supposed to finish 10 minutes ago. But I think it was very valid and very specific questions which needed to be answered. And I'm very grateful to you, sir, for your question. Thank you very much, Mr. Hassan, sir, for your very nice presentation and replies to those questions. So
Thank you.
now we will move over to our next presentation, which is basically on the various types and technologies of hydrokinetic submersible turbines. So this presentation is from Mr. Mohammad Umar Mukhtar. Mr. Umar Mukhtar has done his masters in renewable energy and clean technology from the University of Manchester, UK. He has been a research fellow of energy, transport, environment in SARC Energy Center for the past 2 3 months. He has recently joined us, a very energetic person, and he has earlier done his electrical engineering from the University of near NUS University, Islamabad. He has also worked as an energy consultant in Re-Energia as well as a project engineer in beverages company like Coca-Cola. His passion is for the policy and regulatory as well as the economics of renewable energy. So Mr. Umar Mukhtar would give us a presentation on the various types and technologies of hydrokinetic submersible turbines. And now I will shift over to Mr. Umar Mukhtar. Umar, you are okay to go now. Am I audible to Umar? Umar, can you listen to me? I think Umar Mukhtar has shared his screen, but he's having a little bit issue with his microphone. I think we would be okay in next 10 20 seconds. Let me. I hope all the participants are enjoying this our webinar, the presentation along with the question answer sessions, and we request all the participants, all the presenters, everybody to take part in the question answer session because that's what feedback from your side would be to us. And although and secondly also it would be a learning experience for other participants also if you ask these kind of questions. So you are most welcome to ask any questions, anything you want to ask about the technology aspects or anything like that. uh, Mr. Umar Mukhtar. Umar, am I audible to you? Uh, in the meanwhile, since Umar is having some difficulty connecting to the webinar, we would like to inform all the participants that we would have a very short break session at 11:25 to 12 o'clock. And after that, we have very nice presentations from Dr. Akhtar Nawaz on the topics of assessment of resource potential for selected site and the micro hydro projects best practices and productive utilization in Pakistan from an expert from GIZ Islamabad, Mr. Asif Fareed. Then we would also have we have requested and we have received confirmation from Dr. Carl Comsey from the small hydro.
Hello,
He
SN.
would give. Yes,
Can you
yes,
hear me?
Umar Saab, you are. We can hear you now. You are ready to go. So over to you, sir. Now, please.
Well, thank you very much, and I apologize for this technical problem which I was having because my microphone was not audible enough. I hope that you all can listen to me now and you can see my screen properly. Okay, so thank you very much, Asan Saab, for introducing me. And again, apologies for the small glitch. We'll go over quickly through the presentation to make up for the lost time. Well, as Asan Saab has introduced me, I'm Omar Mukhtar and I'm a research fellow of energy, transport and environment at SARC Energy Center. I have a passion for renewable energy, especially the policy and regulatory aspects of the renewable energy. Going through the presentation, I would be first giving a brief introduction on the hydrokinetic systems. Then I would be giving a small overview of the structure of hydrokinetic power generation systems, then the classification of hydrokinetic turbines, like what kind of turbines exist and what kind of technologies exist. Then we would be going over the augmentation of the hydrocanic turbines through ducts, through the use of ducts and diffusers. Then after going through all these technology options, I would be giving my overview of what is the most viable turbine option. After that, we would be discussing the types of system generators for the hydrokinetic turbines because the turbine options are different, but the type of the generator which has to be put on the hydrokinetic turbine, it is important to look at that aspect as well. And then finally, we would be going through a few companies and technology options which are currently in the market, which exist in the market for hydrokinetic turbines. So moving over to the first topic, which is the brief introduction to the hydrokinetic system. Well, as already explained by my predecessor, Mr. Ehsan, hydrokinetic system is an electrical power generation system which extracts energy from the flowing water of a river or stream, and it produces the quality energy to the utility grid or remote communities. Hydro energy is available in many forms, which are potential energy from high head of water retained in dams, or it could be kinetic energy from current flow of current in the rivers and tidal barrages, or it could be kinetic energy also from the movement of waves on relatively static water masses. The type of system that I would be discussing in this presentation is the hydrokinetic system that is always deployed in the river or tidal environments. For those with riverside homes, small water generators with low head hydropower are the most reliable is the most reliable source of renewable energy because the and it's also important because the variation of water speed is similar to the wind speed. Therefore, the system structure and operation principles are quite similar to the wind power system. Um, Here, I would like to explain this formula often used for calculation of energy flux of the water stream. This formula, as you might have noticed, is also used for calculation of the energy flux for wind energy. So here you can see P relates to the power which which is in expressed in watts. Then rho is the water density. If we use this formula for calculation of wind energy, then instead of water density, we would be using the air density. Here we use water density in kilogram per meter cube. Then Ck is the power coefficient, also called the Betz limit. It actually gives you the extraction efficiency, and the maximum value could be 0.593, which means that the total amount of kinetic energy flowing into a stream, the maximum power that could be generated from that kinetic energy is 59.3%. So this is the theoretical value. Theoretically, if X amount of kinetic energy is flowing into the stream, you can get only 0.593 into times X of that value from that stream. As this is the theoretical value, so the actual value which is realized, actual power which is realized from the streams, it is in actual and all practicality, it is lower than 59.3%. And as Mr. Hassan before me explained, that it is somewhere around the figure of the range of 15% for modern hydrokinetic turbines. Then in this formula, A refers to the turbine area, the area of the rotor blades, and V is the velocity of water in meters per second. A number of different concepts have been developed to utilize this kinetic power throughout the world. Um, there are turbine systems which are considered as prime choices for such conversion, but there also exist some non-turbine options. But those non-turbine systems are mostly at the prototype stage, so we would be only focusing on the turbine options of which use the kinetic energy of the streams. So moving on to the structure of the hydrokinetic power generation system, the overall structure is shown in the form of a block diagram here. As shown, the system consists of a hydrokinetic turbine, a generator, which is usually a permanent magnet PMSC generator, though other types of generators could also be used, but we would be discussing about more in later about that in later slides. Then a power conversion interface is required, and then finally a battery or connection to the grid. When the turbine is merged into the water, the flowing current turns the turbine, and the coupled generator rotor will spin along with the turbine shaft. If an induction machine is used as a generator, then a gear is also required between the generator and the turbine to produce the corresponding frequency during lower water speeds. Um, the the basically the gear is required because the flow of the water or the speed of the water is lower than the that required for generation of electricity. Therefore a gearbox is coupled with the generator so that using it could make use of the lower speed of the water stream. However, permanent magnet synchronous generator is usually connected to kinetic turbines because it does not need a gearbox and it can be connected directly. The output power is controlled and converted by the power conversion interface. And for a grid connected system, an inverter connects the DC bus to convert the DC power to AC power and then exports this AC power to the power grid. But for a standalone system, a local resistor and a battery pack are attached to the DC bus directly. Therefore, you don't need a converter or inverter. The load resistor used to dissipate the extra power produced by the system when the battery is fully discharged, and a suitable load resistor should be able to consume the power on the DC bus without being overheated and burnt off. So you can see that the system of the hydrokinetic power generation is quite similar to the wind power system. Uh, in real systems, for example, the real commercial product, variable frequency drives, which are commonly known as VFDs, is also used to realize the function of power conversion interface. Moreover, the battery pack is also used to power up the VFD generator and some other instruments of the system. Moving on to the classification of hydrokinetic turbines. Um, Hydrokinetic turbines, like windmills, is a rotary engine operating in water as it converts hydrokinetic energy to mechanical energy. Um, the theory of operation is described as the moving water is directed onto the blades of the turbine runner and creating a force on the blades. Due to the spinning blades, the force acts through as a distance and energy is transferred from the water to the turbine. Therefore, different kinds of turbine blade classifications could be used. And this classification has actually been described by or proposed by Mr. Hall. And his classification is being reproduced here for the presentation. The two most common small-scale hydrokinetic turbine concepts are the axial flow turbine and the cross flow turbine. We'll first have a look at the axial flow turbine. So as seen here, the axial flow turbine has a rotational axis of rotor which is parallel to the incoming water stream. Then within the axial flow turbine, there are further classifications such as inclined axis or the horizontal axis. Within the inclined axis turbine, basically they have been mostly studied for small river energy conversions and applications. In both the axial flow horizontal axis and the cross flow axis turbines, the sweep area of turbine tends to be relatively small as compared to the total dimensions of the device. But here in inclined axis turbine, the sweep area of the rotor blades, it is increased by giving an inclination to the turbine rotors. If we expand the size of the turbine, it would lead to considerable increase of the supporting structures and the structural strength at the root of the vertical axis turbine. Hence, the overall cost of the system would be increased. Therefore, the inclined axis turbine, because the turbine's axis, as you can see here, it swings across the pivot on a supporting structure or on a float. So this option reduces the cost, and because of the higher swept area of the rotors, it gives us better efficiency as well. The inclination area of this turbine, it is passively adjustable to the stream speed and is determined by the balance of the hydrodynamic forces, buoyancy, and weight of the turbine. For maintenance axis, the turbine axis swings to near the water surface by being pulled up at the lower end of the turbine using a cable outside the system. So this is very easy to use, but this is easy to use because it is being used for very small power generation applications. So big inclined axis turbine systems are not possible. Therefore, if we are talking about a few watts or a few hundred watts, so this inclined axis turbine is a very good option because it automatically sets its direction towards the incoming flow of water, and because it is movable, so it could be easily moved across for maintenance purposes. Now we will have a look at the horizontal axis turbines. The horizontal axis turbines are very common in tidal energy conversions and are very similar to modern day wind turbines from the design and structural point of view, as you can see here. Horizontal axis.
Mr. Umar, may I intervene? Sir,
Yeah.
I think we are getting a bit short of time. So if you could
Okay.
just wrap it up in next 1 to 2 minutes, we would like to take some 2, 3 questions, and we could give you some chance later tomorrow in some kind of a session. So if you could just wrap it up in like 1 to 2 minutes. Thank you.
Okay, so I'll try to wrap up the classification of the turbines, and then rest of the slides we could present it later whenever we have the time. Okay, so back to the horizontal axis turbines. As you can see that the horizontal axis turbines, they look very similar to the wind turbines, and they are very similar from design and structure point of view as well. Within the horizontal axis turbines, the turbines with rigid mooring structure, they require the generator unit to be placed near the seabed or the riverbed, and the horizontal axis rotors with buoyant mooring mechanism. Within that, we could have either a submerged generator or a non-submerged generator which floats over the water surface. Then the other type is the cross flow turbine. We would have a look at the structure. Here in the cross flow turbines, their rotation axis is perpendicular to the flow of water, and they mostly appear as cylindrical rotating structures. Here you can see the water flow, it actually comes right at the rotating structure of the turbines. Cross flow turbines are less efficient than axial flow turbines. However, cross flow turbines have many potential advantages for marine applications. First of all, the cylindrical shape of the cross flow turbine allows themselves to be easily stacked and arranged in an array within a limited space. The efficiency of each individual cross flow turbine can be increased in the form of a power farm array. In addition, the stacking of cross-flow turbines is allowed to share a common electric converter, and this technique reduces equipment and maintenance costs, which is a very important advantage in hydrokinetic applications. However, some disadvantages also exist. For example, compared to the axial turbines, the cross-flow turbines, they can rotate unidirectionally even with bidirectional fluid flow. Within the cross-flow turbines, now there are in-plane axis and vertical axis cross-flow turbines. So I would be giving a very small, brief overview of these turbines, and then I'll be finishing my presentation. These cross-flow turbines can be divided into the vertical axis, in which the axis is vertical to the plane of water, and the floating and in-plane axis. So this turbine is the in-plane axis, in which the axis of the turbine is on the horizontal plane of water surface, while these are vertical axis. Rest of these are vertical axis turbines, where the axis of the turbine is vertical to the plane of the water. Um, these are mainly drag-based devices and inherently less efficient than their lift-based counterparts. The large amount of material usage is another problem for such turbines. Darius turbines with the in-plane axis may also fall under this category. In the vertical axis domain, Darius turbines are the most prominent options, even though examples of H Darius or squirrel cage Darius are rather common. But instances of Darius turbines in the form of curved blades are also being used in hydro applications. Um, the Gorlov turbine is another member of the vertical axis family, where the blades are of helical structure. Savonius turbines are another example, which are drag type devices, which may consist of straight or skewed blades. These turbines may also be classified based on their drag and lift of the blades, their up and down flow orientation of the rotor, and fixed or variable pitching mechanism of the blades. Different types of rotors may also be converged to make a hybrid, such as Darius Savonius hybrid, in order to achieve a specific performance feature. So with this, I would be ending my presentation. We still have some topics to cover, which is regarding the augmentation of the turbines through ducts and diffuses, the most viable turbine option, types of system generator for hydrokinetic turbines, and then finally the different technologies which exist in the market currently. So hopefully we would be going through that later in whatever slot which I get to present to you guys. So thank you very much, and over to you, Mr. Hassan.
Thank you very much, Umar Saab, for your very nice presentation. Mr. Umar has briefly touched on the technical formulas and the types of hydrokinetic submersible turbines, giving an analogy to the wind turbines, and it was very interesting to see how this formula of wind turbine is also working similarly on this technology, with the density difference being the part. So then he has also touched on the structures of hydro submersible turbines with generators and specific parts. And lastly, he has covered the classifications of the different hydrokinetic turbines available. But right now, gentlemen, ladies and gentlemen, we are a bit short of time. We have two, three questions received from the different participants, but we have thought of giving the line directly to our next presenter, and after that presentation, we will collectively hold the question answer section before the break time. So this would give us some time, and we are lacking behind the time. And secondly, we have a very detailed session on the technical, on the knowledge sharing session at the end, near the end of the second day of webinar. So we will try to accommodate all these leftover presentations and all these leftover materials on the second day. So I think we have a next expert whose name is Dr. Nawaz Akhtar. Dr. Nawaz Akhtar is going to present on the selection of site for hydrokinetic submersible turbines. Dr. Saab's, Dr. Saab has been the key person behind the study and the project of this hydrokinetic submersible turbine. He has done the in-house study back last year, and now he's doing this project as well as a webinar. So I will briefly give an intro of the Dr. Nawaz Akhtar Sahib right now. Dr. Mohammad Nawaz Akhtar is a professional mechanical engineer with masters in mechanical engineering power and PhD in hydrogen fuel cell technology. He earlier conducted a study to assess the resource potential and planning for a demonstration project using run-of-river submersible water turbine. He has extensive experience in the designing, coordination, and fabrication, installation, commissioning of power plants. His professional strengths are mechanical designing, engineering management, technical procurement, technical inspections, R&D in the areas of renewable technologies, specifically PEM fuel cell technology. He holds 5 publications in national and international journals and a lot of conference papers. He first time represented Pakistan in 5 international forums regarding hydrogen fuel cell technology. He is a member of many professional bodies. So, Dr. Saab, we are very thankful to you for agreeing to give presentation on such an important topic. Dr. Saab is going to give 2 more presentations tomorrow and today also. So over to Dr. Saab for his selection of site for hydrokinetic submersible turbines. And Dr. Saab, I would request you to be very brief in your presentation because we are lacking behind in our schedule. So Dr. Saab is going to give his presentation now. Dr. Saab, am I audible to you?
Yes,
Thank you, Dr. Saab, and over to you, sir. Now you can start.
I welcome you all the participants, respected professionals all over the globe, and specifically the member states of South Asian regional area. And my two colleagues have given you a little introduction about the submersible turbines, what type of submersible turbines are, how they work, what are the different kinds of submersible turbines, and how the energy is produced. So, general aspects of the submersible turbines have been discussed accordingly, and after going through the initial survey and decision made for a specific turbine, then comes the site. The selection of site is a very important parameter because the energy extraction from the flowing stream of water is the basic root of this technology. Because as we have learned, the flowing water is the main source of energy through which we have to extract the power. So we have to concentrate on the selection of most suitable site available to us. So we have gone through the desktop survey of all canals and rivers in Pakistan, which can be a dedicated source for the extraction of kinetic power from these rivers and canals. And we made the desktop survey, and then we reached to the final destination of the most available suitable site. So in this session, we will discuss following 4 topics. First is criteria for the selection of a site, and the second is comparison of potential sites, and the number third is result of the selection, and number 4 is description of the selected site. So first of all, we will see that how we conducted the desktop survey and found 10 rivers and 55 canals throughout Pakistan, which can be the potential source for the extraction of kinetic power from rivers and canals. Generally, the velocity of water in the irrigation canals is kept below 1.5 meter per second to avoid the erosion of banks and sides of the canals. But at different locations of canals, the velocity of water increases due to the decrease in the area of cross section available for water flow and inclination levels, etc. Like at the originating points of canals, under the bridges, water level crossings, and distribution channels. Those points are typically most suitable for the extraction of this energy through hydrokinetic turbines. So, going through this desktop survey, we came to the decision that the Ghazi Brotha power canal originating from Ghazi town near to Tarbela Dam was the top of this all 55 canals and rivers we came across. Here we can see the beautiful view of this canal because this canal has been designed for the purpose of potential energy extraction from the water available in Tarbela Dam, and they built this water channel, and 1450 megawatt energy is being extracted through this channel. Now we look at the parameters of this canal. Water flow velocity in it is 1.8 meter per second, which is useful and coming into the range of the water velocity, which is good for most type of turbines. And depth of this canal is 9 meters, which is also very good depth, and up to 8 meter height of turbine or blade area can be accommodated in this canal. And the width of this canal is 100 meters, which is also very good, so that in line we can install many turbines. And length of this canal is 52 kilometers. It means, and that is all with uniform parameters, uniform laminar flow of water in it, and always constant flow, constant velocity, and all guarded across. Both sides of this canal has road access and very good infrastructure available for any project. So we consider this the best available resource in Pakistan. The second canal we came across was Upper Jhelum Canal. This canal has following parameters, which is not ideal, but the second level after the Ghazi Brotha Canal. It originates from Mangala Dam and runs for 127.4 kilometers. The water flow velocity in main canal is approximately 0.9 meter per second. And depth of this canal is 2.86 meters. And width of this canal is 68.6 meters. So this canal has also very huge potential. The velocity in the main canal is not very good, but can be utilized, as specifically as earlier we discussed that under the bridges, originating points, and distribution channels, the velocity of water increases, and that can be utilized accordingly. And our third canal we came across during the survey was Machai Canal, which is located near Mardan in KPK province. And this canal is also very good, having lot of kinetic energy in it, and generally in the main flow the velocity of water is 1 meter per second, and depth of the main canal is 2 meters. Width of this canal is 6 meters, and it runs for 42 kilometers. But as we earlier discussed, that in the consideration of the canal design, to avoid erosion of the banks and sides of the canals, the velocity of water is kept below 1 meter per second so that it remains safe and sides of the canals may not be damaged. So here we can see the waterfall. The purpose of this waterfall is to decrease the velocity of water in it, and it has been created after a certain distance when the inclination of the local area through which canal is running becomes more steep, then such falls are created and velocity is decreased. So these are the three canals we came across, and now we will go for the criteria of the selection of a site. Let me see what could be the criteria for the selection of a site so that we can evaluate the best one resource available to us. So number one is the velocity of water, which is most critical parameter. It may not be less than 0.5 meter per second. Number two is depth of water. The depth of water, as earlier also discussed with our colleague, is critical in a way that the turbine blades might be submerged in the flowing stream of water in the canal or river. Number three is width of canal. That is, the width of the canal or river defines the extent of number of turbines in one array. Number four, consistency in days, means the above mentioned parameters might be available for sufficient number of days and at least 250 days annually. Number five, utilization potential in kilowatt. The possible utilization potential of the electrical energy might be ensured. Either it is domestic, agricultural, commercial, or industrial. Number six, acceptability potential. Acceptability or willingness of the local population or local regional governments and their administrative support might be ensured. Number seven, approachability. The approachability to the potential site for the manpower, machines should be ensured. Number eight, security threats. Security threats involved, if any, during construction and for the life cycle of the plant might be assessed, and as a counter action to safeguard, the required mechanism might be explored accordingly. Number nine, grid connectivity. The available infrastructure near the potential site for the grid connectivity or transmission lines for the end users might be ensured or planned. Number 10, commercial viability. The commercial viability in terms of competitiveness and room for power evacuation and utilization must be available or ensured. So by considering all the parameters, we can make the decision which one is the best available source for the installation of a turbine or a project for hydrokinetic energy extraction. Now, we will compare the parameters of these three canals we have discussed earlier. Here we see one by one The velocity of
Doctor,
water.
excuse me, can I intervene? Doctor, my request to you is please be a little bit swift in going through your presentation because we are very behind the schedule and we would unfortunately would not have enough time for the question answer session. So could
Okay.
you just quickly, briefly,
Okay.
quickly go through your presentation? Thank you.
Okay. So, as we discussed earlier, these are the parameters, and we have comparison of all the parameters among the three canals. So, on the basis of this, we selected the Upper Jhelum Canal regarding all the parameters we can come across, because Ghazi Brotha Canal is the best one, but due to the limitations of the 1450 megawatt of power extraction through potential energy, the process of getting permissions and NOC for this canal was a difficult job, and so that for a kickstart we should start from somewhere. We selected the Upper Jhelum Canal. So now we'll briefly discuss the Upper Jhelum Canal. It is located on two rivers, Jhelum and Chenab, in the north of Punjab province. It runs from Mangla Dam to Chenab River, and floodwater nullas drain through the Upper Jhelum Canal into the Jhelum. It has total length of 127.4 kilometers. It supplies water for two hydropower stations. At Rasool, it is 22 megawatt. At Shadiwal, it is 12 megawatt. Be sure these two power plants are using potential energy of this canal. And the selected site is at head regulator situated at Jagu RD 123000, which is 8 kilometers from GT Road towards Mangla. And there are 4 water level crossings for the flood water nullas on the entire length of the canal. So this is the site, exact point where we have a potential and we can install the submersible turbine. This is Jagu level water crossing, and this is the exact channel which we have selected for the installation of turbine. This is channel number 7 under the bridge, and there are 17 channels under this bridge. Now, description of the selected site. The canal is Upper Jhelum Canal, channel number 7 under the bridge. Velocity of water, main flowing stream under the bridge is 1.08 meter per second, and velocity of water over the slope under the bridge, which is nearly 30 degree, is 3.6 meter per second, and depth of water over there is 1.1 meter, and consistency available is 335 days. So assessment of the possible utilization potential of the electrical energy is, there is a building of this head regulator monitoring station over there, which is a 3 kilowatt electrical load, which can be utilized accordingly. So assessment of the acceptability potential of the local population is also there, because both sides of the canal is thickly populated, and they are eagerly wandering for the uninterrupted source of electrical power, and they will be happy to get if they have any solution like this. And approachability is also good, because there is maintenance infrastructure, metal wide roads, associated staff, thickly populated area around, so, and a good network structure of roads, and every facility is there. So it could be good for the installation of this turbine and this project over. And as a threat, no threat is there, because the area is very good and under control through security agencies, and 220 kilowatt grid lines are also available along the sides of this canal, and this parameter is also satisfied. So we selected this site so that we can demonstrate the technology and attract the stakeholders from government, local population, investors, end users, and academia, so that we can demonstrate and kickstart this start of this technology and utilize this huge potential which is available in Pakistan and rest of the member states of SAARC and throughout the globe. And for this, we have did our efforts, and we also welcome all of you to give us suggestions and share hands with us and to make successful this technology utilization and to progress in this regard. So thank you very much for listening me and giving your precious time. Now questions are welcome if any. Thank you very much.
Thank you very much, Dr. Saab, for your very nice and detailed presentation on the selection of site. And I very much hope that everybody has learned a lot from this very informative presentation. So very quickly, I would brief. Dr. Saab said something about the Ghazi Barota Power Canal producing nearly 1400 megawatt of electricity. Then Dr. Saab has given criteria for selection of the site, which include the velocity, the depth of the canal, the width of the canal, consistency with a minimum number of days, utilization potential, approachability, security threats, grid connection, and commercial viability. So these criteria were very, very important for the selection of the site, as mentioned by Dr. Saab. Then Dr. Saab has also briefly described each specific site, the three selected sites for the project. He has given preview and the overall review of all these specific sites. Thank you very much, Dr. Saab, for your presentation. And now we will quickly move to the question answer session. We are lacking behind the schedule, so we will take not more than 2 to 3 questions. So, Dr. Saab, the first question we will ask you is the first question has arrived from. Uh, the first question is for Umar Mukhtar. Mr. Umar Mukhtar, you have been asked that can it be integrated with other systems like PV, wind into hybrid system, and under what condition it is beneficial, interest of cost and benefit, something like that. Mostly it is related with the question is related with the integration with other systems in a hybrid system. So over to Mr. Umar Mukhtar. Mr. Umar Mukhtar, now you can please reply the question. Am I audible to Mr. Umar? Okay. So let's go to the next question we have from Mr. Umar is going to we will see it also. So Dr. Saab, we have a question, another question for you. In the meanwhile, Mr. Umar Mukhtar, we are trying to catch him for the question. So we will ask another question from you. This came from the Ministry of Economic Affairs, Bhutan. Mr. Chotan Duba, I hope I am pronouncing the name correctly, working in the Department of Renewable Energy under Ministry of Economic Affairs, Bhutan, has asked a question. If you can share us the impact of sediment particles or any other objects that may flow through the turbine and their measures to prevent from malfunctioning. What type of quality of water required for smooth functioning of the system? Doctor, this question is relevant to you. Please go ahead.
Yes. Actually, there are certain debris materials flowing in the canals, and we have to consider and be careful about these, and we have to safeguard our turbine so that the materials which can enter into the blade area may not damage it. So for this, there are different designs available. On the front side of the turbine, they are installed to safeguard the turbine blades from these type of materials. Generally, in canals, the wood particles, branches, leaves, and debris from the greenhouse materials may be flowing in it, and rest is the sand particles, stones, and like this. But during installation, we have to consider the turbine we are going to present next talk is floating type. So in floating type, we can safeguard the sand, stones, and like this because they are on the bed, and turbine is staying away from these type of materials. But the light materials are flowing in. For that, the safeguard has been provided through a cage made of wires, strips, or steel bars, and that is as per safeguard requirements. So these debris may not enter into the turbine of the blades. Yes.
Thank you very much, Dr. Saab, for your very nice reply. And I again request Mr. Chotan Doba that if the relevant question has been answered correctly, if you think if there is any other further clarification required, you can text us. We can ask Dr. Saab in further detail about the question. Meanwhile, Dr. Saab, Mr. Bikash Sharma from EC Mode, the question was earlier answered by Mr. Sanula, but he has referred to you the same question, that what is the minimum depth of canal or stream required to operate this technology? He's from the EC mode. So I would like you to be very brief in your reply, just to tell us what is the minimum depth of canal or stream required to operate this technology.
Mr. Sharma, thank you very much. Actually, the question has been answered the same. The first requirement is the turbine blades must be submerged, and the additional depth of water required is depending on how we are going to install the turbine. If we are going to install the turbine on a stand-alone foundation within the canal, then we have to take care of the design of the turbine, how much height it attains, and plus the turbine structure is accounted for that. So this much height is required, the height of the turbine plus the foundation. And if the turbine is floating condition, as we have in our model here from Smart Hydro, so for that case it is floating over the water. In that case, only the depth of water is required, which is the diameter of the turbine, that is 1 meter. So a little higher than 1 meter is good enough for that case. But if we have more height, it may give us the laminar flow and with a constant velocity. Otherwise, it may have some disturbances near the bed of the river or
Yes.
canal.
Yes, thank you very much, Dr. Saab, for your reply to Mr. Bikash. And I think Dr. Saab also has a very detailed presentation on the planning of those turbines. I was discussing with Dr. Saab about those turbines. He has made a layout schedule of those turbines in arrays and in rows. So I think Dr. Saab will have a detailed presentation on that one tomorrow morning. So now I will quickly go to Mr. Umar Mukhtar for the question asked by earlier by one of the participants. He has asked a question on, can it be integrated with other system, PV, wind into hybrid system, this technology? Secondly, there was another question asked that how much electricity this question can be referred to Dr. Saab. So Umar, you can carry on with this question, please. Can it be integrated with other system as a hybrid one?
Thank you very much for the question. I hope you can hear me now. Yes, it can be integrated with other systems, especially photovoltaics, because as I mentioned earlier, these are small scale turbines, kilowatt or watt level turbines. For small scale applications, for example, powering a single home or a combination of 3 or 4 or 5 homes, as I mentioned in the block diagram, the power output from these turbines, it goes into directly into a battery pack or to the grid. So if it goes into the battery pack, you can always charge the batteries from a combination of either PV or the hydrokinetic turbines. If it goes to the grid, again, integration is possible. So it always depends on the type of the application. It depends on the resource available in that area. And finally, it depends on the integration costs. It was asked if it is beneficial in terms of cost benefit. So yeah, again, it depends on case to case basis. If there is an area, for example, in Punjab, Pakistan, where Dr. Nawaz carried out this prototype experiment. So in that area, there's plenty of sunlight. in the usually more than 1000 watt per meter square. The canals have their floating PV could be used on the canals along with the integration of the hydrokinetic turbines on the bed of the canal. So such an integration of PV as well as hydrokinetic turbines is very much possible from the context of Pakistan and India canal system. But for other countries, again, it depends on case-to-case basis.
Thank you very much, Umar, for the detailed answer to the specific question. So I think we have one more question, but we are going to shift this question to after the break in our next session. So, ladies and gentlemen, thank you very much for listening to this amazing presentations and informative sessions. We ask you to, we will have a very short break of 20 minutes. We will rejoin you at 1200 hours Pakistan Standard Time, and we hope to continue this webinar. Thank you very much, everybody, for your presentations, and thank you very much. Hello, good morning, and welcome everybody to SARC Energy Center's webinar. Now we will restart our schedule. Before the break, we had very brief presentations on the topic of introduction of hydrokinetic submersible turbines from Ihsanullah, various types and technologies of hydrokinetic turbines from Mr. Umar Mukhtar. Then we had a brief presentation on the selection of site for hydrokinetic submersible turbines by Dr. Mohammad Nawaz Akhtar. So after the break, now we will quickly start with our next presenter. Next presenter is also Dr. Mohammad Nawaz Akhtar. The topic of the presentation is assessment of resource potential of selected site. Previously, he has given the presentation on the selection of site. Now the next topic is on the assessment of resource potential of the selected site. So I once again ask all the presenters and participants, if you have any question, you can type it in the text form. You can also raise hand if you want to ask the question verbally. Please, I would like to repeat again that you can also you can also ask the question verbally to us if you raise your hand or write in the text message that you want to ask it verbally. So we will then unmute you and you can ask the question directly to the participant. But of course, you can also write the question as being asked by the other participants. So Dr. Saab, we are giving the mic to you for your presentation. Over to Dr. Saab now.
All the participants from all over the globe and specifically from South Asian countries. So, as Mr. Ahsan Javed has introduced about the webinar, and the topic this time is assessment of resource potential of submersible water turbine. So we have selected the site. Now, before going to install any turbine or to go for the settlement of a project, we have to assess the resource potential of that site. So in this talk, we will go for the assessment of resource potential of the site we have selected so far, which is Upper Jhelum Canal.
Doctor, may I intervene? We cannot see your presentation. Your presentation is not available on the screen.
But from my side, it's okay. Please check what's wrong.
I think Dr. Saab's screen. In the meanwhile, Dr. Saab presentation is being corrected. Dr. Saab, you can start speaking. I think your presentation would be uploaded now.
No, it's okay. इसको minimize कर. Can you see the full screen, Mr. Hassan?
Yes, sir. Now the screen is very visible. You can go ahead. Please continue. Again, sir, Dr. Saab, I would request you to be very quick and brief in your presentation. Thank you very much.
Okay. Okay. As we have discussed, following SARC member states are blessed with a good irrigation canal system. First of all is India, then Pakistan. Moreover, the rest of the SARC countries like Afghanistan, Bhutan, Nepal, Bangladesh, and Sri Lanka has also plenty of rich resources for hydrokinetic energy available for extraction. So as earlier said, and in the previous lectures, that the principle of operation of the hydrokinetic turbines are similar to the wind turbines. And the only difference is the density of the air and water, which is water is 850 times greater than the density of air. And same, the resource in water is 850 times greater than a wind turbine for the same airflow or water flow. Okay. Now, we will consider first of all types of resource potential. First is theoretical potential. Second is technical potential. Third is economic potential. And we will go through all these one by one. First is the calculation of resource potential of selected site, and we will consider the approach how we will calculate the resource potential. Then the calculation of theoretical resource potential. Third is calculation of technical resource potential. Number 4 is calculation of economic potential, and we'll go one by one. And first, the approach is that a survey was conducted to measure the following parameters to assess the potential of electrical power from the Upper Jhelum Canal. Number 1 is flow of water discharge in meter cube per second, and the second is velocity of water in meter per second, and third is depth of water in meters, and the fourth one is availability of water in days over the year. Now, what is theoretical potential? The theoretical resource potential is the annual average amount of physical energy that is hypothetically available. It can be calculated by following considerations. Number 1, average flow rate of water in meter cube per second. Number 2, change in hydraulic head between the beginning and end of the canal are the points of consideration. Number 2. Now we'll go for the calculation of theoretical resource potential of the selected site. Following are the general parameters of the Upper Jhelum Canal. Number 1, the main velocity of water flowing in the canal is 0.914 meter per second. Number 2, velocity of water in the channels under the bridge is 1.082 meter per second. And number 3, number of channels under the bridge is 17 of the bridge which we have selected for this. Number 4, a raised siphon concrete cross section of length 73.2 meter near to jug water level is also available, where small turbines can also be installed, and that may be 114 or like that. Now, these are the existing parameters of Upper Jhelum Canal, and the canal has been divided into two sections due to the reason that both sections have different parameters, and we will discuss one by one. First section is from starting to 74.4 kilometers, and the second section is 74.4 to 127.4 kilometers. The discharge rate in first section is 212.376 meter cube per second, and in the second section it is 116.09. The bed width in the first section is 69.54 meters, and in the second section it is 65.5, a little less than the first section. Full supply depth in first section is 3.2 meters, and in the second section it is 2 meters approximately. Number 3, the slide slope, the inclination level of the sides is 1.5 meter in the first section, and in the second section it is 1. And the longitudinal slope, a head over length, that is 6667, and it is uniform in both sections. Now this is the discharge history of the canal, which is monitored and always available on their website. Then now we'll go for the calculation work. It was calculated based on the data available in the table presented at slide 8, which is coming next. And we have an expression for this, that is theoretical power is equal to gamma multiplied by Q multiplied by delta H, where gamma is the specific weight of water, that is 9789 Newton per meter cube at 20 degrees centigrade. And Q is the flow rate of water in meter cube per second, and delta H is the change in hydraulic head between the beginning and end of canal. And length of canal is 127.4 kilometers of both sections. Now both sections with different geometries and water flow rates, hence we have to calculate the theoretical power potential for the two sections separately. As we discussed, these are the two sections. Now, by putting the values in the equation, we have the theoretical power we get is 23.19 megawatt in first section. Similarly, by putting the respective values in the same equation, we get 9.5 megawatt in the second section. If we sum up these two, and we get 32.69 megawatt, which is the theoretical potential of this whole canal, including two sections. Now, We will go for the technical potential. The technical resource potential is the portion of a theoretical resource that can be captured and converted into electricity using a specific technology. It can be calculated by following considerations. Number one, velocity of flowing water, stream. Number two, width of canal or river. Number three, depth of water. Number four, rotor diameter of the turbine. Number five, inter-turbine spacing in the arrays. Number six, distance between two arrays. Number seven, availability of resource in days. Number eight, system and topographic constraints. Number nine, land use constraints. Number 10, system performance and temperature of water. And we will consider all these parameters when going through. Now, this is the turbine we have selected as a model turbine for the calculation of technical resource potential, as well as for the installation of a demonstration project, first of its kind, being going to install next in Upper Jalham Canal on the site which we have selected and we described earlier. So, first of all is the debris protector. From the front side, if we can see, there's steel cage which is called debris protector. So if any flowing materials are coming from the front side of the turbine, that can be protected from the blades. Then we can see the black color rotor blades. Then is the diffuser body, and top side is floats, and there is float struts, and there are also visible power outlet and attachment points of the floats and generator body and the diffuser body. So these floats are basically designed to keep the turbine floating. That's why we call it floating type submersible turbine, and it is developed and manufactured by Smart Hydro, Germany. Now, due to parametric variations in the canal, we have divided the canal into 4 sections. Number 1 is water level crossing bridges, and such bridges are 4 along the canal. Number 2, siphons. They are 18 in number throughout the canal. Number 3, first section of canal. Number 4, second section of canal. So all these 4 have different parameters. So we have to calculate one by one separately. Now, this is the channel number 7, and this is the arrangement of turbines within one channel of the bridge which we have selected for this study. And 2.5 is the distance between two turbines, and 1 meter is the diameter of the turbine, and 6.1 is the width of one channel. Now, these are the general parameters at this location. Now, the number of channels under the bridge, 17. Channel width is 6.1 meter. Water depth in the channel is 1 meter. Velocity of water in channel slope, that is 3.6 meter per second, because it is around 30-degree slope. So rotor diameter of the turbine is 1 meter. Proposed minimum distance between two turbines is 2.5 meter. Number of turbines in one channel is 2. Total number of turbines under the bridge is 17 multiplied by 2, that is 34. So number of similar level crossings along the canal, they are 4, and total turbines on the 4 level crossings is 136, and we will use this turbine for the calculation of technical potential. So again, coming to the calculation, the technical potential for 136 turbines we have to calculate. Now, if we consider the characteristic curve of this turbine, this is the characteristic curve of this turbine. We see that the starting velocity of this turbine is 0.75 meter per second, and at a velocity of 2.9 meter per second, the curve has achieved maximum power, and then it is stable. So 5 kilowatt can be achieved after the 2.9 meter per second for this turbine, from this turbine. So power produced from this 136 turbines under the bridges can be calculated by multiplying with 136 into 5. That is the maximum power, because the velocity is available for that. So the total power may be 680 kilowatt. So now we'll considering the losses in cascading and transmission. Supposing it may be 10%, so we have 68 kilowatt power maybe slip away. So in this way, we can get 0.612 megawatt of power out of these 4 bridges, and by the installation of 136 turbines. So now we'll go for the calculation of technical source potential on the siphons, which we have discussed earlier. So number of siphons are 18. Velocity of flowing water on siphons is 1.08 meter per second. Width of the siphon is 68.62 meter. Width of one turbine is 1 meter. Proposed minimum distance between two turbines is 2.5 meter. And number of turbines proposed in one row, that can be calculated. And simply by dividing, the 2.5 is the distance between two turbines plus 1, the diameter of one turbine, we get 19. So length of the siphon is 91.5 meter. So proposed distance between two rows is 15d. Here d is the diameter of the turbine. So after every 15 meter, we can install another row of turbines on the siphon. So total rows of turbines may be 91.5 divided by 15. It becomes 6 rows. So number of turbines on one siphon is 19 into 6, and number of turbines on one siphon is 114. In this way, total turbines in 18 siphons may be 2052. So this is the siphon, and the arrangement of turbines over the siphon, we can see maybe it is not exactly, because we have to shift their center of one turbine to the next row. So, but just to give you an idea that the turbines can be installed this way. So by using the proposed model turbine, we have seen so far, so rotor diameter is 1 meter and maximum power is 5 kilowatt. So reference characteristic curve of this turbine, and in the previous slide, yes, we can see here that at this velocity we can have around 200 watt, because the starting point of this turbine from where it starts working. So the output may be low, but for the calculation purpose we use this model turbine. So the expected power from this turbine may be 200 watt. So total power from this siphon can be 200 multiplied by 2052 watt, that is 410 kilowatt. So losses in cascading and transmission at the rate of 10%, that may be 410 minus 41. So 369 kilowatt may be the output power from this siphon, and the total power may be 0.36 megawatt. Now we come to the technical potential in the first section of main canal. The designation is PM1 technical. So technical potential canal of 74.4 kilometer area. So first section of this canal. So velocity of flowing water is 0.91 meter per second. Width of canal is 68.62. Depth of water in canal is 2.86. Number of turbines proposed in one row is 68.62 divided by 2.5 plus 1, that is 3.5, maybe 19. So proposed distance between two rows is 30d, because here the velocity is less. So 30 into 1, that is d is the diameter of the turbine. So this much 2480 are the number of turbines in the length of 74.4 kilometer, or 74,400 meters. So number of rows missed by roads and bridges at the rate of 10% may be 248, and number of rows accounted for in siphons, that is 6 rows multiplied by 9 is equal to 54, because we have considered 9 siphons in the first section and 9 section in the respective section. So in this way, number of rows accounted for under bridges is 4, and net number of rows in this canal area may be, by adding up 248 plus 54 plus 4 and subtracting it from the total number of rows, that is 2480. So we get 2174 number of rows in this canal area that can be counted for the installation of turbine. So number of turbines in first section of the main canal is 2174 multiplied by 19 number of turbines in one row. So total number of turbines may be 41,306. So these are the uh, overview of the turbines that could be installed in the way. It is not exactly that, but just to give the view how these turbines look like when they will be installed along the length of the turbine, length of the canal. So by using the proposed model turbine, which is rotor diameter is 1, maximum power is 5 kilowatt. So reference the same characteristic curve we have seen earlier. The water velocity is 0.91. Expected power from this turbine is 200 watt. Total power from first section is 200 multiplied by 41,306 watt. That becomes 8261 kilowatt or 8.26 megawatt. So losses in cascading and transmission at the rate of 10% is 8.26 minus 0.826 megawatt. So net power from first section is 7.43 megawatt. The proposed schematic arrays of turbines in the main canal we have seen. So technical potential in the first section may be 7.43 megawatt. Now we come to the second section of the main canal, and that is running from 74.4 kilometer to 127.4 kilometer. It becomes 53 kilometer or 53,000 meters. So velocity of flowing water is same. Width of canal is 65.57 and depth of water is now 2 meters. So number of turbines proposed in one row is 18. Proposed distance between two rows is 30d, which is 30 meters. And number of rows in 53,000 meters of length of canal is 1,766. So number of rows missed by roads and bridges at the rate of 10% is 176. And number of rows accounted for on siphons is at the rate of 6 into 9, that is 54. So net number of rows in the second section of canal may be 1536. So number of turbines in second section of main canal becomes 27648. So by using this same turbine, we get the power in the second section is 200 multiplied by these number of turbines, that is 27648 watt, and it becomes 5529 kilowatt, and as a total it may be 5.53 megawatt. So losses in cascading and transmission at the rate of 10% is 0.553 megawatt. So net technical potential in the second section is 4.98 megawatt. Now total power from main canal, maybe adding up these two sections, PM1 and PM2, that is 7.43 plus 4.98 megawatt. So it becomes 12.41 megawatt in the main channel. Now by the adding up the power produced from all the four sections, we get 0.612, that was under the bridges, and 0.36 megawatt, that is on the siphons, and 12.41 megawatt, that is in the main sections of the canal. So net resource potential of this canal becomes 13.38 megawatt. So this much power can be supplied to, if we consider 2 kilowatt at the rate of 2 kilowatt, because it is villager around the canal. So 2 kilowatt may be good enough for a small house in villages. So 6,691 houses can be given power from this resource. And if we give to cottage industry at the rate of 20 kilowatt, then 669 cottage industries can be furnished. And if we give the power to the tube wells, then at the rate of 20 kilowatt to each tube well, 669 tube wells can be facilitated through this electrical power produced in this canal through kinetic energy. Now we consider the economic potential by considering number one, projected cost of the project, number two, projected power from the project, number three, availability of water resource in days, number four, availability of plant factor, number five, upfront tariff, number six, annual O&M cost, number seven, annual revenue, number eight, annual profit. Now, as we have calculated the projected power from the upper Jharkhand canal, that is 13,380 kilowatt. if we multiply it with 24 hours, because it is hours, that is kilowatt hour. If we multiply with 24 hours, so then it becomes this much figure, that is 13380 multiplied with 24 into 300 days, because for 300 days this much power may be available. So for microhydro power plants by NEPRA, the tariff has been given, that is 12.7 Pakistan rupees for per kilowatt hour unit. So by multiplying this figure with this, we can get 1223.46 million Pak rupees. And if we convert into dollar, presently 1 Pak rupees is equal to $1 is equal to 110 Pak rupees. So by this we get 11.12 million US dollar. So this is much potential can be harnessed through this canal. So for hydrokinetic power plants, the average equipment cost is for these small turbines from $3 to $4. So if we are going for megawatt, it may be $4 million. The project cost at the rate of 50% of the equipment cost, because for transportation, installation, infrastructure, and all these adding up, it can be 50% of the equipment cost. So by having this much, we can have installed cost of the project, that is 13.75 into 4 into 1.5 million. So it becomes 82.5 million US dollar. So in this way, annual O&M cost of the project, that may be 2.4% of the project cost. So in this way, we can have US dollar 1.98 million of O&M cost. So in this way, annual net profit may be 9.14 million US dollar, and if we convert into Pakistan rupees, that may be 1005.4 million. So economic resource potential of the canal may be 1004.5 million, and total cost of the project divided by annual net profit, we can get the payback period, that may be 9 years, which is a reasonable period over the project life cycle in this regard. Now, we have just used a simple generic model for the calculation of hydrokinetic resource potential of any site by using the same equation and putting the equation in Excel format. We can get easily how much theoretical potential this site or this canal can give us. Then similarly, the economic resource potential can be calculated, how much kilowatt we have multiplying by 24 hours, or how much hours are available, and D is the number of days, and the tariff, that is 12.7 here. It can vary from site to site, and in this way we can get the total economic potential. So this is over as far for the short time available. So I have gone through quickly. Now if any questions are available, I am available to answer. So thank you very much, and now the mic is handed over to Mr. Ehsan Javed.
Thank you very much, sir. Thank you, Dr. Saab, for your very informative presentation. And Dr. Saab, in his presentation, has briefly touched three very important aspects of the project installed, which include theoretical, technical, and economical potential. In the theoretical potential side, Dr. Saab has given overview of the selected sites, theoretical potential. Then based on the equation, Dr. Saab gave a certain figure of the whole canal which was evaluated, something in the range of 30 megawatt. Then on the technical potential side, Dr. Saab has referred to a turbine by the Smart Hydro manufactured in Germany. And then Dr. Saab has given four very important aspects of the technical potential of the canal, including under bridges, the two sections of the canal, and the siphons. Then lastly, Dr. Saab has touched economical potential of this canal, which to my understanding comes nearly in range of 8 to 9 years. So Dr. Saab, thank you very much for your presentation. It was wonderful listening to you. So now quickly we move on to the question answer session. So anyone interested may ask questions. They can also write questions to us So we have our question from Mr. Taimur Jamil. He has asked a question from Dr. Saab. Dr. Saab, what is the level of expertise required to install projects based on this technology? Please, very brief in your questions. Thank you.
Thank, welcome. Uh, the level of expertise depends on the kind of turbine you have. For example, the type of turbine we have so far, this, it can be installed without any special expertise, and because this type of turbine is floating type. So you have to just put in the flowing stream of the canal or river and tie up with the bridge with the help of ropes, and you can see the attaching points on the top under the floating conditions. There are two strips having holes, so just have ropes tie up from the 4 points and then join it to a single rope and then connect to the foundation of the bridge or any temporary foundation you can create on the within the canal, or you can hold a rope along the side of the canal and hook up more than one, two, three, or any type depending on the width of the canal. You can have installed this turbine, and then as soon as the turbine is within the water, it starts generating electricity, and then you can independently use it to the resource to the user point for any utilization, or you can integrate with through it, or depending on the utilization procedure.
Thank you very much, Dr. Saab. I think in his brief answer, Dr. Saab has indirectly referred that in South Asia region we have enough expertise to deal with this novel technology. With the experience we have in the hydropower sector in South Asia region, all the member states are sufficiently resourced and they have the capacity to deal with the implementation of this technology. So this is not a kind of a very advanced technology. So Dr. Saab, thank you very much. We move on to our second question, which is do you know who are the main manufacturers of these turbines? And I suppose that these turbines are mostly developed abroad. So if you can name a few, two, three companies which you have, which came to your knowledge about the for the manufacture of these turbines, sir.
Okay, thank you. As the technology is new, but considering the potential and the future market, lot of companies are underway, and some companies are in commercial level. For example, this smart hydro, which is German based, and Verdant Power, that is USA, Open Flow, that is Sweden, and the Canadian water flow, and there are many numbers, and from all countries, all developed countries, they are struggling for it, and around 44 manufacturers we have the list, and we'll show you in the next lecture tomorrow. And mainly we have this turbine from Smart Hydro, that is German based.
Thank you very much, sir. I think what we can do is if the participant is very interested, he can write a very short email to us and we can send him back with the list of the approved manufacturers or whatever information we have. We would be ready to share this information with anyone who is interested in. So, Dr. Saab, very last question. We are short of time, so we will address this last question is from Mr. Bilal Hussain, who is in National Transmission in Dispatch Company, Lahore, Pakistan. So his question is the operation maintenance of such plants difficult compared to other power plants? Dr. Saab, over to you.
Yes, exactly not. These turbines are very simple in construction and operation, and mostly they are installed in isolated areas, and their construction is very simple and rugged, and they don't need any maintenance over the years except the connecting points and the infrastructure and battery banks, and if it is a hybrid system, then the rest of the things. But in the case of turbine, it is over the years, it don't need any maintenance or any monitoring or any supervision for it.
Dr. Saab, thank you very much for your brief review. Ladies and gentlemen, we have like 2, 3 minutes more. So I would continue with one more question from Dr. Saab. Dr. Saab, to your knowledge, who are the main experts on this technology in South Asia? I'm not sure you are well aware of other experts in the region, and you can name few experts in, if you have any
Yes,
knowledge of that.
yes. Kirloskar is the Indian company, which is in line with the Japanese company, and they are also manufacturing the submersible turbines from the kinetic energy utilization. Kirloskar, this is Indian company, and they have a joint venture with Japanese company. Mr. Hassan,
Thank you very much, Dr. Saab, for replies to those questions. In the meanwhile, we would urge all the participants to please ask questions, whatever questions you would like Dr. Saab or other panelists to answer to your queries, clarifications. We are ready to respond to those questions. And now I think we are over with Dr. Saab's session. And on our schedule, the next presenter. First of all, I would like to personally thank Dr. Saab for his very informative presentation and in very informative session of question answer session. Thank you, Dr. Saab. We will again connect with you during your next presentation, maybe tomorrow morning or maybe at the end of today's session when we are holding the question answer session. Thank you very much, Dr. Saab.
welcome.
So So thank you very much, ladies and gentlemen. Now we move on to our next presenter. Our next presenter is Mr. Asif Fareed from GIZ. And his topic of the presentation is micro hydro power best practices and productive utilization in Pakistan. And what we thought is that let's carry on with the introduction of Mr. Asif Fareed. Mr. Asif Fareed is a mechanical engineer and currently working as a technical advisor at GIZ Renewable Energy and Energy Efficiency Project. He is having over 10 years of experience in renewable energy technologies, especially in promotion of micro and mini hydro power in northern part of Pakistan. He has conducted more than 50 micro hydro power projects technical assessment for various GIZ partners. GIG partner in organizations all include Alternative Energy Development Board Pakistan, AKRSP, which is Our Khan Rural Support Program, Pakistan PPAF, and Sarhad Rural Support Program, and University of Ghulam Ishaq Khan Institute, Topi, and PEDO in Swat, Mardan, Gilgit, Baltistan, and Chitral. Very extensive experience working in northern areas of Pakistan. He has also provided capacity building training to the field engineers on testing of MHP's performance and provided recommendation on quality improvement aspects of MHP sector in Pakistan. So we would listen to Mr. Asif Fareed for his presentation on best practices and productive utilization in Pakistan. So Mr. Asif Fareed, this mic is over to you, sir.
Uh, Thank you very much, Hassan Javed, for giving me time. That I will just show you a slide over here. Uh, is it okay that this one?
Yes, sir. Your presentation is visible to everyone, and I think your
Okay.
voice is very clear. Please go ahead.
Okay. Thank you very much. So my name is Asif Fareed. I am working as technical advisor in GSI Renewable Energy and Energy Efficiency Project. So as I mentioned, I have more than 10 years of working experience with GIZ. So GIZ is mainly working in Pakistan, and it was initiated in 2005 with a focus to promote renewable energy technologies and industrial energy efficiency. The main counterpart of for the project on behalf of the government of Pakistan is Ministry of Energy and Alternate Energy Development Board. The program is supporting its partner both from the public and private sector for the promotion of renewable energy, especially solar energy, micro hydro, and other policies initiative in Pakistan. So today I would like to give a short presentation on the very important topic like micro and mini hydro. What are the best practices and productive utilization based on our working experience in the northern part of Pakistan. So let me start with the first slide. As you know, that there is a huge potential of large and small hydropower exists in northern part of Pakistan, whereas the southern part of Pakistan is having a solar and wind potential. So as per data collection from various sources, there are over 860 projects installed so far in micro and mini hydro, and there are more than 600 projects are in pipeline for installation. And in the northern part of Pakistan, especially Gilgit and Baltistan and also Chitral, there is national grid is not available. So that's the only source of electricity they are using from the mainly from the micro and mini hydro. And so as a next slide, you can see what are the existing known information we have available with us. Like PEDO is the Pakhtunkhwa Energy Development Organization from the KPK. So they have recently initiated implementation of 356 MHPs, and they are covering 12 districts of KPK. They have chosen 7 implementation NGOs. So more or less, they have already completed this project. And EU is also implementing few of the 240 MHPs in KPK. They are implementing these MHPs through SRSP, and then CDM is Clean Development Mechanism that was initiated together with PPAF and World Bank funding. Then they choose an implementation NGO like AKRSP. They have installed so many projects in Gilgit, Baltistan, and Chitral. And KFWO and PPF also implementing another type of project, 5 MHPs in 3 districts of KPK. And they have chosen 3 implementation NGOs, SRSP, AKRSP, and others. So there are also new project initiative that is PEDO is planning, that is ADB funding, that 672 projects they will install in 19 districts of KPK with the same 7 implementation NGOs. So there are also many other projects, but these are the known information which we are working with them, but there are private and NGOs and other small projects, many existing. So as a development of turbines or technology, or you can see that the turbine concept was mainly arises from the water wheel concept when people were using mechanical power for the wheat flour grinding in the old times. And also there are different model of turbine have been developed on the basis of head and flow. That's low head, you see there's a Kaplan turbine, then turbo turbine is also used, and for high head and low flow the pelton wheel turbine is used. And the normally more or less in Pakistan mostly the people are using this cross flow turbine technology for even low and medium and high head, because it's a certified technology available in Pakistan. There are other technologies also available. I have put some Dropbox link at the downside of this slide where you can see this the hydropower scout guide. It's developed by a German expert who was also working in Pakistan, but when he visited outside other countries, then he developed and shared with us this hydropower scout guide, which is very useful for the project planning. It covers all aspects of planning, designing, installation, civil work, and each and everything. So as a next selection of turbines that based on the head and also suitability upon performance. So for the Kaplan, it's a low head turbine. Then cross flow, it's a medium head. You can have cost effectiveness and also efficiency varies in time to time. There are other turbine that is also known as Pico cross flow turbine. That's a very small kind of turbine. It's 1 kilowatt or 2 kilowatt. You can also generate it, suitable for low head and also for canal falls. So propeller turbines and Francis turbines widely used in international and other countries, and also sometimes people are importing into Pakistan because this Francis turbine technology is not available in Pakistan. So Pelton turbine is also having in the Skardu region, Baltistan region, there are the water flow is very less, but the head is very high over there. So people try to develop their own technology as a reverse engineering, but still they are suffering for their low efficiency, but still they are getting their output power. So the last one also this kinetic submersible turbine that's use kinetic energy flow of water. That is should be if there is greater than 2 meter per second, that is very good. But in Pakistan there are very less technologies available in Pakistan. You have to import it from the outside the country. But to import such kind of technology, it will cost you a double or triple. And then there is also a huge potential for this kinetic energy turbine because the widespread canal system, irrigation system, having a great slope over there, you can easily install, and it's a very simple design, little civil work required, and easy operation and maintenance. But to do some such kind of kinetic energy turbines technology in Pakistan is really a big challenge for all of us. And so I give you a very simple example of one of this Pico crossflow turbine that just for the example you can see that there are uh, this turbine is easy to install, small canal, and then the whole slide almost give you each and everything kind of information which is useful for the project developer. Similarly, we wish that the other type of turbine, the submersible turbine and the kinetic turbine, that can also be produced some kind of same brochures, materials, or slides, or for dissemination purpose. So within one slide, you can see that having a 500 watt to 2000 watt capacity, and it requires 6 meter head at least minimum. The size of the runner is very small. It's 100 meter. So 100 millimeter, and then these turbines were actually manufactured by one of the local manufacturer in Texas that he did some kind of testing and also produced some kind of turbine. Usually the students of the universities, they oftenly do some kind of research project, and it is very useful for them. So as a next step, on the what is our role, GSL role in promotion of hydropower. So on the request of our partners, we have initiated some pilots for utilization of surplus electricity from the MHPs for economic development. That is called productive use of renewable energy. But we observed that there are overall quality aspects issues of MHP's development, which has become a challenging task for the project developers, equipment supplier, and community operators who do not have sufficient technical and management capacities to ensure sustainable electricity generation from the MHPs. At the same time, it has been realized that economic and financial sustainability of the rural electrification need enhancement by the promotion of productive uses. So we did some kind of productive utilization promotion, introduction of swimming flour mills and sawmills and other things, that whatever the surplus electricity available that can be used. But we observed that these are the most of the units were failing because of voltage fluctuation, and turbines were not performing well. Therefore, we decided to do some kind of technical assessment of to shortlist some site. So you can see from this slide, although GSZ has facilitated the local turbine manufacturer for technology transfer a certified T15 type cross-flow turbine, but adoption of this technology was a big challenge. Therefore, people prefer to install the old technology based on reverse engineering design. In order to shortlist few of the MHP sites for pure activities, we have conducted technical assessment in different regions. The key findings of the study indicate that most of the surveyed MHPs have lower output than claimed by the design. This is mainly due to inappropriate design structure, control mechanism, inadequate turbine technology use, as well as overall design and ineffective management. So this slide shows the region Chitral, which have been covered by us in 2012 when we did some technical assessment. So from the graphic, you can see the output, from the first one, like 200 BREP MHP was having 200 kilowatt capacity, but when it was tested with the dummy load, it produces up to 123 kilowatt. So in the green at the down bottom, you can see that it was running at that time at daytime about 12 o'clock, about 50 kilowatt. This means that there are still surplus electricity available that can be used for productive utilization. So this, all the sites covered in Chitral area. So there are few of the sites which you will be surprised that the capacity showing very high, but actual testing and other things were done in such a way, and also it produces very less output power. This means that because of the equipment was not working very well. Maybe the turbine is having issues, or water is less, or the design and other all of those parameters. So, meaning to say that there are issues we have seen, we have shared with the partners the same. Then the things were quite improved, getting improved. So these are the graphics. Also, you can see that the hourly load curve. You can check here that if you start with the curve that within 24 hours of load. So in summer season, this is the first side, that 200 kilowatt BEF MHP load curve. So it can generate more than like 20 from starting at 12 o'clock midnight, then up to 24 hours. It can show different kind of graphics. So you can imagine that in summer there are low demand, but in winter there are high demand because of heating and other load. So I will share with you this presentation, then you can easily understand. The similar kind of technical assessment we have done in MHP Skardu region. So you can see the same kind of result, but it's quite better than the Chitral region. So this is one of the site in 160 kilowatt MHP site in Dapa Skardu. That is, you can see the detailed analysis. We produce some kind of detailed report, but one of the table I have taken from the report. So from the report, you can see this table that surplus electricity is available with 70 kilowatt from this project. Then production in the June 2012, when we noted down from the kilowatt hour meter, it was running 593 hours for 1 month. Then average load was 53. Still, you can see there are surplus electricity available for this. This was the one of the best site in Skardu region. So there are common issues observed during MHP assessment, mainly control system not working properly, voltages fluctuation, insufficient install capacity, some of the MHP not operational, transmission and other issues, and then alignment, vibration issues, and also you can see belts and pulleys, civil structure, and variation in design and parameters. So after highlighting all those issues, the organization, have started to adopt the new technology of T15 turbines. So they have mentioned in their even tender document that they need the certified technology along with electronic load controller, and to supply stabilized electricity, and that has been so far adopted. And I will like to show you some of the success in the P15 cross-flow turbine technology, and that was one of the project first project done by SRSP in Kailash Valley, Chitral. It's 100 kilowatt, two turbines that was installed in Chitral, and both the turbines are having a very good output, and both the turbines were having a very good output. We have tested these turbines with our latest equipment, and then it was quite a good result we have achieved from these MHPs. And then they are also using these MHPs for hotels, electricities, and also productive utilization. Um, and then so far, just to highlight that what are the done has been done so far, and what are the difference it is making the new turbines technology. So it's about 25 to 30% better efficiency. So far, we have received the information. 270 projects have been installed, and leading by the two manufacturer, Hydrolink company in Texla and Mukhtar Engineering Works in Bardan. The total cumulative capacity is about 17 megawatt so far has been installed in different region of KPK and also Gilgit-Baltistan. So because why you choose this, typical technologies, standardized or certified technologies, because it is having a, pre data sheets and also spreadsheets to calculate. And with this graph, you can easily, one graph, you can easily calculate your power, for example, on head. If you know the head about 40 meter, then if you have a discharge, then 450 liter, then you can easily calculate the power. It's about 100 and something, 105 or 125 kilowatt you can easily get. And also this graphic gives you what will be the width of the runner and dia of the runner, and also different aspects. So I have also put Dropbox link down, so you can easily download the literature about this T15 or other type of turbines. So support on MHP efficiency testing, that I think my last slide over here. So we have, because we have installed more than 270 MHPs, and then implementation of testing and commissioning protocol is very important. So we have decided to again support PEDO, because PEDO recently requested us to do some kind of measurement of the installed MHP. So we have decided to hire international consultant to visit Pakistan and do provide training to the PEDO's engineers and representative, and also turbine manufacturer, to review the design of the few of the turbine and test it with their equipment. Is it as per standards of intact or not, or still if there is any recommendation for improvement, we can still do. About 25 representative of PEDO will be trained hopefully in the month of April or May. We are planning to do that, and contract is already in process. So there are key challenges which we mentioned that, okay, this challenge, one of the challenge will be addressed. Testing and commissioning protocol will be developed by this consultant, and then maintaining data logs and proper monitoring is also very important. That you should have a registers available in powerhouse to have a proper data for last year, hourly load, or at least kilowatt hour consumption, load pattern, and other, if there is any issues or suggestion or any repair and maintenance done, it should be properly recorded on the data register. Then the facilitation for the MHP turbine testing or third party verification, it is also very important that we should have some kind of things available. That, but unfortunately in Pakistan there are no as such third party verification system. But PEDO, I think they have mentioned in their tender document that they will release the payment only once they have third party verification that the 100 kilowatt turbine really produce 100 kilowatt. Otherwise they will not release the full amount to the manufacturer. So they are planning to have some kind of third party verification system, and then also our consultant will provide them the training. Some of the project developers still uses low cost approach, result in poor quality of turbine. The other turbine technologies like T15, okay, we have the certified, but for the Pelton, for the Francis, and other type of kinetic turbine, these should be also certified, or they should be certified manufacturer or having a joint venture with the international company so that production can be started in Pakistan. And productive use is also a very important aspect that if you have turbine and then you are running it, and then at the daytime if you have a surplus electricity it should be used as a for productive uses, then you can generate income, then you can with the income you can run other businesses and also do some maintenance and repair work and make a payment to the operators and other things. So introduction of also submersible turbine I have mentioned there. The technologies for the canal using kinetic, because we are talking so much on the other technologies, but so far when we talk about this kinetic energy turbine or small turbine, this submersible turbine, then sometimes people ask that, oh, why not you have to do some kind of fulfill the already existing potential of run of the river in Chitral and other areas, that there is a lot of potential. First, you have to fulfill that one, then you can also talk about the other technologies. But these are the things we are facing. But hopefully, we will do some kind of research work as well as on the other type of technologies. So as a to share just knowledge sharing that we had developed some kind of hydropower documentaries that community-based rural electrification. So you can click on the link and you can watch those documentaries. It gives you overall MHP scenario in Pakistan. Also, we have specifically developed another documentary on specifically on productive use of energies. What are our success in the northern part of northern part of Pakistan, that's mainly in Chitral area. So best practices, operation maintenance, manual, and also you can find a lot of information from Energypedia wiki. For you need to sign up once with your Gmail account or other email account, then you can easily get this information. You click on the link, then you can easily got all the information. MHP article we have wrote, and also some kind of Dropbox link for MHP Pakistan and other things. So I think this is all from my side. If you have any questions, you can ask me, and then I will be happy to respond on this topic.
Thank you very much, Mr. Asif Farid, for a very informative and detailed presentation on slightly a bit off the road topic. And I would like to brief a little bit about the participants for asking presentation about MHP experience in Pakistan. With the GIZ's experience of planned projects and funding given to MHP projects in Pakistan, and with the R&D and local manufacturing facility available with the locals, plus with the expertise available in Pakistan for training, manufacturing, testing facility of this micro hydro and mini hydro power projects in Pakistan, we felt that the same could be replicated for these submersible water turbines, which should be a kind of a localized and more indigenous model. I mean, importing 1, 2 turbines from abroad couldn't solve the problem of South Asia in the future, where you need to manufacture and develop these technologies on a much larger scale if you need to implement this. So, with this, I would briefly touch on few topics shared by Asif Farid. He has in his presentation given a potential of 3000 megawatt of MHP, and with a very staggering number of projects installed in northern areas of Pakistan in the tune of 860 projects, and the pipeline projects are still 800 projects, which is a very large number. Secondly, the projects were implemented in coordination with GIZ and localized implementing partner like PDO in the northern area of Pakistan. Funding was also available from EU, World Bank, and Pakistan Poverty Alleviation Fund and Asian Development Bank. Plus, few of the projects were implemented through Clean Development Mechanism of United Nations Framework Convention on Climate Change. Then he has briefly touched on the different turbines available for micro hydro power projects. One thing I would like to highlight is that community-based projects have been very successful in northern areas of Pakistan comparable to other regions of Pakistan. and micro hydro has been very successful model. Then Mr. Asif Farid touched about the 200 kilowatt MHP load curves, which showed low demand in summers and high demand in winter, which is very obvious due to the cold temperatures and climate in those northern areas of Pakistan. Then he has mentioned some common issues which were observed, to which I would like to emphasize on the voltage frequency fluctuation and the control systems, plus other ones. Then he has given a preview of 100 kilowatt two turbines installed in Chatral and the success story of those turbines. And he has also given some preview on the testing and the efficiency facilities available in Pakistan for these micro hydro power projects. So thank you very much, Mr. Asif Farid, for your very nice and informative presentation. Now I would quickly jump to a question asked by Dr. Shoaib Ahmed. He has asked a question that with this sponsoring these different MHPs and other projects by GIZ, will the GIZ be willing to sponsor in future the submersible water turbines in Pakistan or maybe other South Asian region? I would like to call you to comment on the Pakistan perspective, sir. Please.
Yes, actually, from our side, GSC always work with partners. So our main partner, Alternate Energy Development Board, whenever they have requests to us, then we are willing to do some kind of innovation. But there should be some lead partner, that someone is already leading. Then we can contribute towards in the technology upgradation or whatever. Like similarly, we are now active to provide our support in PEDO for MHP testing, because they are already implementing projects. So there is a need, to develop some kind of testing and commissioning protocol. So we think that it is very important topic that we can provide support when they are asking us that, okay, you have to provide a new technology transfer facilitation. Then our answer is like the local manufacturer, they are now capable to have their own technology cooperation, deals, because they are having money, they are running their business. Earlier, when we did some technology cooperation transfer in 2009, there was nothing. These manufacturer was out of the money, and then we facilitated them on the request of Alternate Energy Development Board. If there is any specific request from Alternate Energy Development Board, then we can definitely provide support also on this submersible technologies or whatever. So
Thank you very much, Mr. Asif Farid, for the consumption of all the other participants. By Alternative Energy Development Board, he meant the Pakistan's federal department, basically responsible for making policies and regulatory frameworks for renewable energy projects in Pakistan. So, what Asif Farid meant is that that agency or any federal agency in other member states could be contacted and they could help in producing the necessary changes in the policy or the regulatory framework required for the implementation of this technology in future. So with this, Mr. Asif Farid, thank you very much for your presentation, and we had a wonderful time on this question answer session with you. We would have liked to continue with this question answer session, but we have Mr. Karl Kompsey from Germany connected with us. He is going to give us the. So first of all, thank you very much, Mr. Asif Farid, for your presentation,
okay,
and thank you, sir.
thank you very much.
So with this, now we actually move on to our next and last presenter for today, Mr. Dr. Karl Kompsey from Smart Hydro. Dr. Karl Kompsey actually studied agricultural and philosophy at the universities of Hamburg and Göttingen. I hope I'm pronouncing the word correctly, Germany. After his PhD, he has spent most of his professional career in the energy business, first as consultant at AT Kearney, later as manager at E.ON, Europe's largest private utility. And he is also a member of the board at Schmack Biogas, one of the pioneers of the biogas market in Europe. In 2009, Karl Komsey has been nominated professor for energy management at Applied University of Kufstein, Austria. His main areas of academic work are international energy markets and renewable energy. In 2010, he founded the Smart Hydro Power to focus on the design and commercialization of kinetic pico hydro power systems. with main focus on rural electrification for emerging markets like India, Latin America, and Eastern Africa. Today, smart hydropower offers complete solutions for distribution generation and for off-grid solutions. So, Dr. Carl Comsey is connected with us. So now I will shift over to Dr. Carl Comsey for his presentation on applications in canals using example of cooling water in thermal power plants. So over to Mr. Carl Comsey. Dr. Carl, can you listen to us, sir?
Yes, I'm listening. That's very nice.
Welcome, sir, and please continue with your presentation, sir.
So, thank you very much. Do you see my screen or don't you?
I'm sorry, but we are not looking at your screen right now. Uh, yes,
Now
it's yes, it's perfect. It's visible to us. Yes, it's visible to us, sir.
You're not seeing the screen?
We are looking at it, sir. It's okay now. We are looking at your screen now. It's okay.
Wonderful. So, good day to everybody. Thank you for the invitation. And I know you are listening from different spots. It's snowing in Germany. This is why I was slightly late for the prior presenter, which was very interesting what I heard. Now we are changing a little bit the topic. While whatever other hydropower technology needs quite a bit of infrastructure and needs a head, so to accelerate the flow through the tube, whatever turbine comes after that, now we are talking about kinetic hydropower. Kinetic hydropower means that you are using the natural flow only, being it canals or rivers. This as well means that we are talking about smaller plants. I'm going firstly to present the company, then I'm jumping directly into an example, and after that I show the market potential in a more general way. Who are we? We are still a startup company from Germany. No Germans beside myself working with us, so it's quite an international group coming from all over the globe. We are founded mainly by German capital, including the KfW, which is a German development bank. You heard already a presentation of the GIZ, so again, it's a German development bank, which does not mean that we are funding our own projects. We always have to look for capital in the private market. What we do is we design, build, and commercialize kinetic hydropower integrated in systems, in mainly hybrid systems for distributed generation and for microgrids. The project I want to present is a project in a cooling tank behind a thermal power plant. It's a coal power plant in a huge mine. So that's a typical application of our technology. It's installed in running water. The plant is never shutting down the cooling canal of the mining plant. The plant is grid synchronized, which means the plant load factor is much above 70%. So we are not talking about off-grid. We are talking about a complementary power plant to a larger power plant, giving low voltage power for all the low voltage application of the plant. It's renewable based 24/7 because it's hydro. What we installed is 20 kilowatts installed capacity, and our generation costs are below $4 per kilowatt hour compared to whatever other renewable technology, grid type technology. This is well below. Compared to photovoltaic, it's more or less 70% of the photovoltaic generation cost compared to small wind. Small wind, it's about half of it or even less. How does kinetic hydropower look like? In our case, I admit this is our plant. There are few other uh, fabricators of kinetic hydropower. It's still a very innovative and new technology. We are doing small standardized plants, small meaning 5 kilowatt each unit of an underwater generator with a permanent magnet, so you can work as well in not grid tied environments. We are using a gearless driven generator because this reduces the need of servicing and maintenance. It's a maintenance free application. The only servicing is cleaning, as always, with hydropower. Why have we chosen such a small plant? Because many times the flow is not higher than 2 or 2.5 meters per second, not the volume, the velocity, and many canals are only 1 to 2 meters deep. So we are using a standardized solution which can be applied in a modular way. That's very important because standardization, you heard in the previous presentation, he briefly talked about the possibility to make it a locally fabricated unit. This is possible. Today we are fabricating in Germany. We are assembling in Germany using components from Hungary, from China, from all over the globe. You could do the same in other countries as well if there is sufficient market. The most important characteristic of hydrokinetic, you see in the power curve on the left, on the right side below the picture. This is the power curve. It shows the dependency of power output to velocity. Velocity measured in meters per second and power output in watt or kilowatt. So it's a non-linear function. As more velocity you have, you finally get the maximum output, which is 5 kilowatt in this generator. You could build larger units, always considering the depths of the canal or river and the velocity. So you can adapt it slightly to local environment. But very important is to understand that power output always depends on velocity. It's different from all other hydropower where you have a certain volume stream and a head. In our case, kinetic hydropower means you have nothing but velocity. You are working with velocity, and it has to be enough to cover the blades of the turbine. In our case, this is 1 meter. So it's 1 meter diameter. It's very small. It's a completely sealed generator. It's aluminium. It's coated, so you can work also in blackwater or in water which is slightly polluted. So the generator will stay there forever. The only thing you have to do is properly clean it. How does that look like in real life? In a commercial application, this is a site-specific structure. So what they did in this site is they build up a simple steel frame. You can do that much easier than they did, but it's a mine, so they have enough money. And remember, it's still below $4 per kilowatt hour. They build up a site-specific structure. They can lower each turbine into the canal, not necessary because you don't need it, but they can do that, and they can generate the electricity. They can even, if they wish to, level up one of the turbines to do some servicing, cleaning, whatsoever. What you see here is there's no debris protection or something similar in front of the turbines because it's not needed. It's a canal, so it's completely clean. There's no need of any debris protection. In this case, you can use simply the water running in the canal. The electricity scheme is interesting because remember, in a normal electricity scheme, what you do is inject on the mid voltage level. On a kind of traditional hydro is going to the 1.2, 1.8, 3.6 kilovolt level. We are staying on the low voltage, so we are very close to all the demand, which is up to 400 volts. We are not talking about megawatt, we are not talking about hundreds of kilowatt, we are talking about community systems and low voltage applications and we are injecting close to those low voltage applications, which as well means that the grid structure is stabilized by the turbines because we are generating 24/7, different from PV or wind, which are fantastic and easy, but not 24/7, which means they always give a certain challenge to the grid. Different from that, hydrokinetic, easily to install, does stabilize the grid. It's an application mainly for the low voltage if you are not getting to much larger plants beyond the 50 kilowatt. Again, a photo, how does that look on the plant? It's very simple to install. What you see here is dump loads, because in case the grid is down, you have to do something with the generation. You see standard inverters, so all that can be again bought locally. The alarm system is something we build up together with the mining company with local resources. You see a simple alarm in case the grid goes down. So the only two situations where you really need servicing of the plant is either the grid goes down, and if you do not have any alternative usage of the energy, then you have to shut down the plant. It's done automatically, but you have to control it that it's really done. If not, inverters could be broken, as with all other electrical plants. And the other is if there is some debris in the water, you need to have a servicing cycle. You need a cleaning cycle. What have we seen after 3 months running? Firstly, we really seen that it works 24/7. This is very important. It really works as it was supposed to work. It's a complete 8,760 hours in a year solution. Again, this is important for the grid and it's important for the generation because you get low cost generation. We've seen that in the canal, the flow is highest in the center. So therefore, we are generating differently with the turbines on the edge than with the turbines in the center. That could be done slightly more intelligent by having a different kind of structure employed in the canal. It depends on the flow of the canal and the easiness to employ infrastructure. In our case, as mine, they have all the tools there to employ a simple infrastructure. So it was easy and inexpensive. In other cases, you would not employ such an elaborated infrastructure, but go for something more easy even. So the second is we've seen quite a bit of turbulences. The reason is that the infrastructure in the water is not completely hydrologically optimized. So you could easily use a different kind of steel, a rounded steel, instead of flat steel, so you have less turbulences, which facilitates a second row of turbines behind, approximately 50 to 75 meters behind the first row. So you can not only use the canal once, you can use it in rows, lining up each 75 to 100 meters. So you can really add up to the generation capacity which is already installed. There is a simple design, and if you look at the design, you see that A, as I already explained, you can install several lines, and B, as you easily see on the first, above in the picture, in the drawing, you see that you could not only use one line of a row of turbines, but if the canal is deep enough, you can go with the second line of turbines, the second row of turbines underneath the first. So the modular system, the modular design of this turbine allows to really employ exactly what the specific site allows you to employ. So if it's 1 meter or 2 meters, it is one single line of turbines. If it's 4 meters or even more, you can employ a structure which allows you to have 2 rows not behind, but above each other, which duplicates your generation capacity. What is the market? I was asked by the organizers to mention the market potential of this distributed generation. Again, it's kinetic hydropower. What you need is canals and rivers. And in East Asia and Pakistan, there are tons, there are millions of canals. You have, I think Pakistan is the country with most fast running canals in the world. And there are many other countries that have already employed hydropower plants or other kind of generation where you could use the tail race or the freezing canal of those existing power plants. So there are different kind of situations. You can use tail races, you can use cooling canals, irrigation canals, if they are running faster than 2 meters per second. Again, it's not the volume, it's the velocity that is needed. And certainly you can use natural rivers. I have only put one photo underneath, which is a photo where you see two, it's from Latin America, two very simple boats taking a turbine, a river turbine, which is now not a submerged, it's a submerged turbine, but not a fixed installed turbine, but a floating turbine in a river. This is something which can be employed off-grid, which is easy to install even in small villages with 100 inhabitants, 200 inhabitants. And again, you can install 1 or 2 or 3 or 4, and the local people do the servicing in this kind of community projects. It's without any need of infrastructure, so it can be done even in the most remote places. To conclude, the market potential is distributed generation using existing infrastructure in whatever canal, as long as it runs fast enough, and rivers, as long as they are running fast enough, but even with lower velocities, because in these off-grid environments, the generation cost will be always below the generation cost with a diesel, not mentioning the environmental impact. I'm leaving you with my contact address. We are currently still in Germany. We are keeping the German fabrication site more as an R&D site, and we are looking for partners in regions giving a license to use the turbine. We are doing training. We are already doing this in Latin America. We are already doing that in India, and we would be keen to do that also in other regions of the world. Thank you.
Thank you very much, Dr. Carl Comsey, for your very informative and detailed presentation. I think you gave a very detailed overview of the application of these turbines in the canals and other applications where they could be used. To summarize a little bit, Dr. Carl Comsey has in the start given a general review of his company with the design and builds and commercialization aspect of his company. Then he took a cooling canal of a coal power plant as an example, whereby he has installed 5 kilowatt turbines, 5 kilowatt turbines with a total generation of 20 kilowatt turbines, and the generation cost of that is at 4 cents per kilowatt hour, which is very impressive. Then Dr. Saab has also informed us about the site structure, where he has installed steel structure for that one. Then he touched a bit on the low voltage application of this technology. Then lately he said something about the technical optimization of this technology with wake effects and the subsequent diffusers which could be used for that one. And he also said something about the reducing the turbulence in the canal, and the flow velocities have to be on the certain level. Then he mentioned some very important point. If the depth of the canal is above 4 to 5 meters, so you could also use arrays of turbines on top of each other. Then he mentioned at the last about the market potential. He specifically mentioned the canal system of Pakistan, and then he mentioned that there could be these turbines could be used in the irrigation canals, plus they could be used in the thermal and chemical power plant canals. Velocity for the irrigation canals should be above or equal to 2 meters per second, while the turbines could also be used in the rural electrification. Lastly, Dr. Karl has also offered his help, and he also offered the South Asian countries that he is willing to licensing for other countries and willing to go and develop these technologies in other countries. Which we are very thankful to Dr. for his nice views. So, Dr. I will quickly jump to the question answer session. I'm sure there will be many questions for you. So, firstly, we have a question from Mohsin from Pakistan, and he has asked that, Doctor, what is the expert level of how do you see the expert and manufacturers around the globe, since you have been developing and installing this technology for a long time and you are in the business for a long time? So, give your very brief comment on the current expertise and the manufacturers around the globe for this technology.
Well, it's not really true that we are in the business for a long time. We have founded the company in 2010, and it's an innovative model. So we are in the business for 4 years now. So we really started in 2014, coming up with a new and updated version of the turbine. Currently, we are focusing in 3 markets, which is Peru, Colombia, and India. This is where we do have today existing partners. These partners do start fabricating in their countries. It's today, none of them does fabricate generators locally. The generators still come from an Hungarian company, but we are doing tests how to use a generator with a gearbox, knowing all the issues with gearboxes, but we have found a generator with a gearbox which runs more than 100,000 hours. This does allow, using a gearbox, to really use locally fabricated generators. And then the only, let's say, piece of IP, intellectual property, that comes from us is how to put together and to perfectly seal a standard generator and a gearbox. So this is a very, very important bit of intellectual property that we are happy to share, and we are happy to look for different generator fabricators, which is not done yet. What is done today is that all the steel work is locally fabricated.
Thank you very much, Dr. Kaul, for your nice reply. Doctor, we have another question from one of the delegates from Ministry of Economic Affairs, Bhutan. He had earlier asked a question, and we have asked reviews from our experts also. But I would like to put up this question to you. He says that share us the impact of sediment particles or any foreign particles which may flow through the turbines. And you should also keep in mind that in these canals in Pakistan and other South Asian region, there are some foreign particles also flowing in the water. What would be the impact of these on the turbines or the sediment particles on the turbine?
The main effect is that you have to change the blades more often. It's exactly the same that happens with traditional hydropower. In case you have a lot of sediments, sediment is something you cannot you cannot catch at the wreck. So it has an impact on the servicing cycle and the maintenance cycle. In our case, the blades are changed locally. It's not done by us. You don't need an engineer. It's something that a trained person, even without any technical education, can do. And the cost of a blade is €90.
Thank you, sir. Thank you very much. Sir, yes. We have another question from Mr. Madhu Hettuwal. He has not mentioned his origin country, but he has asked the question: can we use the turbine at reverse flowing turbulent flow in mountainous area? I think he must be talking about the Bhutan area and Pakistan northern areas where there are mountains and the river flow is very turbulent. So can we use these turbines in those areas?
As long as the river is 1 meter deep and we are completely covered with water, it's possible. the one thing that has to be done, and I'm referring now not so much to Pakistan only, but specifically to Bhutan, which I know a little bit, at least better than northern Pakistan, which I do not know. In you have during the melting period, you have a lot of stones running down the rivers and canals. So what you have to do is you build those turbines with a debris protection into the water, and using the debris protection, you can, I'm going to show you again the debris protection. This is, if you look at the picture, there is a debris protection, and with that debris protection, you are hindering stones of getting to the blades. In these rivers, with a lot of stones being carried down, you have, during the dry season, you have to take away the stones again. So during rainy season or melting season, you do not have any problems with the stones in front of the turbine. But this is all. The the turbulences alone, as long as there is enough flow, do not really hinder the employment of kinetic hydropower. It's turbulence if, like, directly behind a hydropower plant, in the tail race of a hydropower plant, you have turbulences caused by the diffusers of the hydropower plant that are going in the opposite direction. So they are hindering the flow. These turbulences are different. So as long as the turbulences are always kind of directed into one direction, you do not have, they still push the blades and you do not have problems. But once you have turbulences going in the opposite direction, then you do not have the same kind of flow.
Thank you very much, Dr. Saab. I think you gave a very detailed reply to the specific question. And I would quickly jump to the next question. This is from Dr. Shoaib Ahmed. And he has asked a question that what will be the rusting effects on the machines if they are deployed in water? And the connecting question to this is the typical lifetime of any project or machine based on this technology. So you can connect these two questions together, rusting effects and the overall lifetime of this project.
Well, remember, we have started in 2010 and we are still a young company, so there's nothing employed yet longer than 10 years. Our first turbine was employed in 2011, and that turbine still lives. So the turbine design is made for 20 years, and different from photovoltaic, there's no decreasing period. So you do not get less generation capacity after 10 years, because the generator either works or doesn't work. And as long as it works, it works. We do have very low RPM. We are talking about round per minute. We are talking about 250 in the peak, with 5 kilowatt, 250 to 275. The normal generator turns with 1,500 to 2,000 RPM per second. Ours turns with 250 to 275. But the entire design of the generator is the same. So it's made for at least 20 years, even under full capacity. With regard to corrosion and whatever water effects, the seals will hold for 20 years. What is needed, if the water is highly, let's say, polluted, if it's not clean water, what is needed is to repair or to refurbish the coating. The generator comes coated with a marine coat as the blades, which are aluminium blades. So everything is coated, and in case it's not, they are either more often taking out of the water, therefore you have a higher grade of corrosion, or the water is more aggressive, then what you have to do is service the generator and repair the coating of the generator.
Thank you very much, sir. We have, sir, one question from our main panel of experts, Dr. Akhtar Nawaz. He would like to ask you a very specific question related to Pakistan or other South Asia regions. He has, his question is that the irrigation canals carry velocity of water which is less than 1 meter in Pakistan, which intention is to keep the canal sites safe from erosion. So if can you increase the gear ratio in your generator to use these irrigation canals with less water velocity? For example, less than 1 meter per second. For example, for sake of example, we can say if we have a water velocity of 0.75 meter per second. So can you increase the gear ratio of the generator to still produce some output out of that one?
Let me firstly comment, as you explained at the very beginning, I'm an agriculture engineer by education. Irrigation canals should have a little bit more than 1 meter. They should have between 1.2 to 2 meters per second, so you have less sediments. Because if not, you have a sedimentation problems. I still know that there are many irrigation canals running below 1 meter. What you can do if they are very large, let's say you have a typical irrigation canal with 10 meters width and 3 meters depth, you can um, you can reduce the diameter of the canal, which means the same water volume is passing through less diameter, which accelerates the water velocity. So you have higher velocities with the same water volume.
Thank you very much, Dr. Kal, for the reply. We have another question from one of the participants, and he has asked a question that are your products currently available in South Asian countries? Any agency or something like that? I mean, is particularly interested maybe for future importing of your technology in this country. I think that's the main intention behind this question.
Well, into Southeast Asia, we are only exporting at the moment. If there's any market with specific market volume, we would be happy to build up a partnership. But we have worked in many countries. I mean, we are currently discussing a large project in Malaysia, and we would be happy to do other projects in that region. So we have imported to Laos, we have or exported, sorry, we have exported to Laos, we have exported to Indonesia, we are exporting to Malaysia. So we are experienced exporters, and this is always done with the view, with the perspective of building more things locally.
Thank you very much, Dr. Karl. I think we are over with the question answer session with you, and I think it was very informative and very good to have spoke about different aspects of this novel technology with you. And I think we are going to collaborate with you in future too about if we arrive with any query or any clarification, and you could be one of the very good asset for our South Asia region in future, sir. So thank you very much. Let me thank you again for your very nice presentation and for giving us time for this important webinar and considering this in your busy schedule. I really am thankful to you, sir.
Thanks to everybody. Thank you for listening and looking forward to doing projects together.
Thank you, sir. Thank you. So, ladies and gentlemen, it was all for the first day of the webinar. We had now I would like to wrap up the session. Actually, we had been asked one other questions, but we have already covered all the questions during the presentations. But if you think that you need to ask some other questions relevant to these presentations, also you can send us via text. You can also email us. We will get back to you with the replies from our expert in due period of time. But never forget, we have another day of the webinar tomorrow, which will start specifically at 9 o'clock in the morning, and it will end by 1 o'clock in the evening. So just to wrap up the today's one-day webinar, we started with the introduction of the hydrokinetic submersible turbines by Mr. Ehsan Marwat. Then we had a session on the various types and technologies of hydrokinetic submersible turbines by Mr. Umar Mukhtar. Then before the break, we had a session on the selection of specific site for the hydrokinetic submersible turbines by Dr. Mohammad Nawaz Akhtar. After the break, we had a very detailed session on assessment of the resource potential for those selected sites by Dr. Mohammad Nawaz Akhtar. Then we had guest speaker from GIZ, Mr. Asif Fareed, who gave a detailed, informative session on the best practices and productive utilization of micro hydropower projects in keeping in view the perspective of this submersible water turbines. Then lastly, we had a session with Dr. Karl Kompsey from Smart Hydropower Germany. He gave an example of a cooling canal in coal power plant where he has installed these submersible water turbines and these application of these turbines in the canal, and he gave very detailed overview of the technical issues related to these turbines and their implementation issues. So, ladies and gentlemen, it was very wonderful session with all the experts. I am very thankful to all the experts for joining us in this webinar and giving these detailed presentations. And I'm also very thankful to all the attendees, the participants who participated in this webinar, who listened to this very informative webinar. And I urge you again to ask questions, to write us back and give us feedback in form of your text messages, or if you want to give us feedback through email, you are most welcome to do that. And we will tomorrow once again continue with the rest of the presentation. I would just ask my colleague to upload the latest agenda of tomorrow's presentation on our SARC Energy Center's official website, which is www.sarcenergy.org. You can access the latest agenda for tomorrow's webinar on our website. The tomorrow's we will start the day by opening remarks and the agenda recap. Then we will do detailed presentations on the planning for installation of hydrokinetic submersible turbines by Dr. Nawaz Akhtar. Then we will touch the commercial aspects of hydrokinetic submersible turbines. We have a short interview by Mr. Trey Teller from Verdant, USA. Then we would have a business perspective of hydrokinetic submersible turbines. We also have an expert from Italy, a manufacturer of Wind City company, to Mr. Tommaso Morbiato, who will give detailed presentation on the design concepts of hydrokinetic turbines and the performance in variable flows. After the break, we would have separate session with Mr. Irfan Yusuf, Dr. Irfan Yusuf from Alternative Energy Development Board, Pakistan. He will give a perspective of the policy challenges and the regulatory frameworks required for deployment of this technology. And lastly, we would have a simulation studies session with the expert Mr. Asim Shehzad from International Space Technology, Islamabad, Pakistan. And the most important session would be at the end of the webinar, which would be a knowledge sharing session. We would like to increase the time length of this session to include as many question answer sessions, question answers from your side, and to make it as interactive as we can. And then we would conclude with the recommendation and closing of webinar. So thank you very much again for joining us in this webinar. I am now officially closing this webinar, and we will see you tomorrow morning at 9 o'clock. Thank you again. Thank you very much. Bye bye.